Yeah.
I think we can start. Yeah.
Yeah. At the outset, I request all the participants to mute their audio and video during the program. I also request Dr. Suresh Das, professor at IISER Trivandrum, to deliver the welcome address and introductory remarks. Sir.
Thank you, Joshi. On behalf of the committee for organizing the JNCASR and FCBS workshop for college chemistry students and teachers, it gives me great pleasure to welcome you all. All those who would have attended these meetings previously would have known how much of an impact these workshops have been having in chemistry teaching, especially in this state. This, as most of you know, this is the 20th workshop, and unfortunately, due to the pandemic, we have to hold this online. This also happens to be the first workshop that we are conducting after the demise of Professor N.V. George, and so it is an opportunity for us to pay homage to him. Yesterday, when we had the Professor George Memorial Endowment Lecture, which was instituted by Professor C.N.R. Rao and Mrs. Indumati Rao, both Professor Rao and Mrs. Rao had indicated their interest to attend this program today, especially since they have not missed a single FCBS workshop. They have been attending each and every one of them. But unfortunately, as many of you know, a very close and dear friend of theirs, Professor Rodam Narasimhan, passed away yesterday, and there is a condolence meeting which they have to attend, and therefore, unfortunately, they will not be able to be with us today. On behalf of all of us, I take this opportunity to express our deep sorrow on behalf of the FCBS and that FCBS community for the passing away of Professor Rodam Narasimhan, and also our deep appreciation for all the contributions that he has made to science and also to the country. With these words, I would like to speak about the FCBS. And as you know, the FCBS was something that was initiated. It was a brainchild of Professor N.V. George. And it has been a great fortune for people in this part of the world that Professor George and Professor George and it was a great fortune for people from this part of the world that Professor George and Professor C.N.R. Rao shared an enduring friendship which started in IIT Kanpur and continued all these years. And because of this, many things happened in this part of the country. And as you know, the first and foremost, of course, the most important point was that when Professor George retired from IIT Kanpur, he decided to come to RRL Trivandrum and start the photosciences and photonics, what was then as the photochemistry research unit, which later went on to become the photosciences and photonics division. And subsequently, of course, the involvement of both Professor George and Professor C.N.R. Rao, we saw a huge transformation of the institute, was at the Regional Research Laboratory, which is today known as CSIR-NIIST. And of course, all of us also know the role that Professor George played when he tried to get Professor Rao to set up an institution, the Indian Institute for Science Education and Research at Trivandrum. And many of us had the good fortune of seeing this place much before the buildings that we see here had happened. And it is so this enduring friendship that Professor George and Professor Rao has had has indeed benefited the state in many ways, especially in terms of education and specifically the chemistry. The FCBS, of course, as many of you may know, we started in 2000, and we had Professor C.N.R. Rao as the president and Professor N.V. George as its executive director. And it has been one of the most active foundations ever since its establishment, and something that Professor George was very strongly dedicated to. And we have so far conducted more than 20 FCBS lectures for postgraduate students in colleges across the state, and for which the resource persons were very often provided by Professor Rao. And then we had also organized, I think most of them in Trivandrum, with the exception of few which were held in Kottayam. We had organized about 19 JNCASR-FCBS workshops for college chemistry students and teachers, which this one is a part of. And more importantly, these used to be associated with the special lectures for school children, which used to be delivered by Professor C.N.R. Rao and Mrs. Indumati Rao. And these were extremely popular, and many schools used to approach us for the opportunity to send their students to these lectures. And I'm sure that all of these had a significant impact in promoting science and chemistry in this region. As most of you know, the FCBS, the major idea that Professor George had when he established the FCBS was to bring together students, researchers, scientists, and mentors under the same roof. And this was done. Also, the programs were very serious and they were conducted in a very timely manner. And also, the atmosphere of a relaxed atmosphere, which allowed the students and teachers and scientists to mingle together and learn from each other. These were really exciting meetings, which were eagerly looked forward to by all the participants. I am just sharing with you some of the pictures from these events, which has been prepared by Dr. Joshi. And you can see the variety of students and colleges, participants that we had from various. Yeah. Okay. Yeah. So we had. I just want to share one of the FCBS meetings where Professor Rao happened to be with us, and on his way to the airport. That is when he came to. That is when we came to know about the fact that he had been awarded the Bharat Ratna, and the next year, of course, the next FCBS meeting we celebrated this. And these are some of the pictures of that event. As I also mentioned, these FCBS lectures were associated with special lectures that Professor Rao and Mrs. Indumati Rao presented to school students. And Mrs. Indumati Rao inevitably talked about the lives of many great scientists like Faraday and others. And Professor Rao used to touch upon a variety of topics, whether it was graphene, nanomaterials, and all of this was very exciting and stimulating to the students. And you can see some of the pictures from these events here. Let me talk a little bit about Professor George. I'm sure that all of you are eagerly waiting for the lecture, so I don't want to take too much time. Professor George, of course, was a great scientist. Without doubt, he was a great teacher. But the most important fact that at least when we think about Professor George, was of him as a mentor. There are many kinds of mentors. Yesterday, we had a very good talk by Professor Balasubramanian on what mentorship means. And of course, Professor George exemplified many of those qualities of a mentor. But in many ways, he was also a different kind of mentor, because it was not something, Professor George was not like somebody from, not like somebody who was speaking from, yeah, I'm sorry for the confusion. So, yeah. So, of course, Professor George was not somebody who, was someone who was looked at as somebody with a lot of expertise who wanted to share his expertise. But he was someone who actually took great pride in the fact that those whom he mentored or those whom he was associated with were successful. In fact, Professor George was one of the most, Professor George was one of the most happy persons that I have seen. And that was because his happiness came from the happiness of others. It was, if you just wanted to see him excited, all you had to say was talk to him about the success of one of the former students of the group or success of some of the scientists of the group. And that is what made him the happiest. And he was actually personally a very a shy person, even though I would say so, although everybody looks at Professor George as somebody who was a very tough professor. But anybody who knew him closely knew that he was not, he was very self-effacing in many ways. So I have here two quotes which I would like to share, which I feel depicts Professor George and the type of mentor that Professor George was. Yeah. So one is from Benjamin Disraeli, who said, the greatest good you can do for another is not just to share your riches, but to reveal to him his own. I think this is a very good description of Professor George. And the other is that true leaders don't create followers, they create more leaders. And I think this is, in a nutshell, describes what Professor George was to many of us. And he was able to find good in people, even when they were not able to recognize it in themselves to begin with. And that is what encouraged them to do well in life. And there are many examples of this. So if I were to talk about that in chemistry terms, the only example I can see is that of a dendrimer. You know, as you see, you can expand its reach as a leadership develops. And you can see that today, the program, the entire FCBS is inaugurated by the second generation. We have Joshi Joseph from NIIST, we have Reggie Verkis from IISER Trivandrum, and Subbi George from JNCASR. And that has reduced us to the role of observers today. And these are all, when we started FCBS in 2000, with Professor George started that, and we were helping him. These are all students. And today you can see others also in the pictures who are contributing in many other ways in taking the legacy of Professor George forward. And I hope that the FCBS, it's unfortunate this year happens to be a pandemic, but I hope in the subsequent years, this will flourish, and we hope that it will flourish beyond chemistry and in the years to come, it will also increase its reach. And I think this is the best we would be able to, way that we would be able to contribute the legacy and memory of Professor George. And with these few words, I will close my talk and thank you all for your attention. I would, of course, also take this opportunity to thank Professor C.N.R. Rao, who has, as I mentioned, been an enduring friend of Professor George, and of course, whose enormous support has made these FCBS programs so successful. And thank you very much. And with this conclusion, now it is my great pleasure to invite Professor Ajay Ghosh to chair the next session. I think Professor Ajay Ghosh does not need any introduction to this audience or to any audience. He is one of the most well-recognized chemists in the country, and he has been the director of CSIR-NIIST for quite some time, and he's leading it ably and in the true spirit of Professor George and Professor Rao mentoring another new generation of scientists. With these few words, now I invite Professor Ajay Ghosh to chair the next session. Thank you.
Thank you, Dr. Das. Friends,
Stop sharing.
can you hear me?
Yeah, we can hear you.
Yeah. Okay. Dr. Das, Joshi. Yeah, I can see Ramaya suddenly coming in. So Ramaya, Raji, Uday, and other colleagues, friends, students, other invitees, ladies and gentlemen, good afternoon. So as Dr. Das mentioned in his opening remarks, we are conducting this workshop in a rather different mode and different mood. For the past several months, you know, we have been doing this kind of exercise and we learned a lot. How to sit at different places and have discussions, workshops, meetings, conferences and all. Again, as Dr. Das mentioned, you remember that every year we used to have a very vibrant physical FCBS meeting where large number of students and college teachers and other researchers, teachers and all come together and had a lot of discussions, a lot of excellent lectures by our colleagues. And the main attraction was, of course, Professor Rao and Mrs. Rao in all these meetings. They used to come invariably. So this time we are losing one of the very prominent figures of this workshop, this meeting, Professor M.V. George. So as Dr. Das said, this is the first meeting without Professor George's presence. But I'm sure that he will be always associated with this. I don't think he can be separated from this meeting. He will be always with this meeting, and I'm sure he will be enjoying this from another world. Today we have another bad news. Professor Rodan Narasimha, one of the greatest scientists and teachers of this country, today passed away. So my heartfelt condolences to his family. So as usual, after the introduction, we directly go for the scientific presentations, lectures. So this time also, we have a number of people who have been giving lectures to the benefit of the students. So in the first scientific session, we have 3 of our colleagues talking to us. The first talk is by Professor Uday Maitra. I'm sure there is no need for introducing Uday Maitra to this audience. He is, what should I say, he is a default member of FCBS meetings. And it may not be an exaggeration if I say without Uday Maitra, there is no FCBS meeting. So he volunteered himself, every year come here and then interact with the students. He is known for his popular science lectures, particularly to the students community. And also is well known for his experimental demonstrations, which really attract the attention of students and make them more enthusiastic about science, particularly chemistry. So I'm so glad that Uday Maitra is here with us to give the opening lecture of this workshop. And he will be talking to us on determination of organic reaction mechanism. Uday, are you ready?
Yes, I am.
Yes, then proceed.
Shall I share my screen?
Please.
Okay.
So you have 1 hour, Uday.
Yes, I have set my timer as well. Let me see if I can, how do I share? I will share my, right.
Yeah.
Are you all able to see the test slide?
Yeah. We can go to the, yeah, it's
okay.
fine. Yeah.
Okay, all right. So that means everything is working. And what I will do, I will switch off my, my video so that there will be no bandwidth compromise. Let me see, how do I do that? Yeah, let me stop my own video. All right. Yeah. Oh, I'm sorry, there is something There's a scratch somehow coming here.
How this is happening? I think earlier when Dr. Das was also.
This was part of the JNC's, logo. I don't know how this is appearing here. Because it's not in my PowerPoint.
So sometimes it happens with Zoom. Someone can.
Let me unshare.
So Sunoj said that he can resolve it. Sunoj said just send a message.
Okay. Let me unshare and share it again. And yeah, in my PowerPoint it's not there. So let me share this one once more, and hope that this will go. I was getting worried.
Hey, Reggie, can you make Sunoj also host?
Okay. So are you able to see this now?
Yes.
Okay. So thank you very much, Dr. Ajay Ghosh, for the kind introduction. I would also like to thank Dr. Das for setting the stage right for the 20th FCBS meeting. I would like to dedicate my talk to the memory of Professor M.B. George, whom I had known for close to 4 decades. I would like to say a few things about my association with Professor George before I go to the subject proper. I first met him in the second year of my master's at IIT Kanpur. In the first year, he was on sabbatical. I didn't take any courses from him, but I did meet him a few times. And when I came back to India towards the end of 1987 and joined IIT Kanpur, he, in fact, was my mentor. And he provided a bench in his laboratory. And I remember that at that time, Dr. Ramaiah, Dr. Pratapan, and Dr. Munir, they were finishing up their work with Professor George. And I was working alongside these 3 gentlemen and started doing my own independent work, the first few reactions. So that was done in Professor George's laboratory. And he retired in that year, 1988. Throughout my short stay in IIT Kanpur, I used to talk to him very frequently, and he would give many advices. And this continued even after I moved to IISc Bangalore. And of course, as you know, that after the FCBS was established, I was quite frequently attending the FCBS JNCASR meetings. And in addition, I participated with Professor Job in the day-long workshops held all over Kerala. And this is a map of Kerala in which I put these little spots. In many places, I went more than once with Professor George and with some of the senior colleagues who are in the audience. And in fact, this continued even after Professor George stopped, traveling within the state. My latest visit was another place earlier in the February. And I think I can say that, I know more chemistry teachers in Kerala than in any other place. And this was always a very, very enjoyable experience. There are many fond memories associated with my interaction with Professor George in in many occasions. This is a November 2007 academy meeting in NIIST Trivandrum. And we always enjoyed, interaction with him as families. It was really, really nice. And we will miss Professor George, of course, but it's very nice that these 2 great friends decided this event, and Professor Rao has agreed to have it online this year. This is a picture in which Professor George looks a little embarrassed. Some of you perhaps remember that this was on 4th of October 2009 in, I believe, Lake Palace Hotel in Alleppey. And it was one day after his 81st birthday, and there's a birthday cake that you see. And such situations always made Professor George a bit, nervous, and perhaps that's the embarrassing look that you see on his face. So what I would like to do today is to talk to you about something that is not unknown to any of you. I would like to speak about organic reaction mechanisms and in a topic with a historical perspective that I believe Professor George would have liked, because some of the developments that I'll speak to you about today were in fact established during the time when Professor George had initiated his research and his independent career. So this determination of organic reaction mechanism is something that is extremely complicated, although when we study, when the students are taught reaction mechanisms in the high school level, they always start pushing the arrows and believe that when they push the arrows, that's the ultimate truth. Interestingly, the real story is different from that. So I would like to give you a perspective about one component of how one can proceed in understanding organic reaction mechanisms. I should perhaps point out that I'm not talking about my own research. I'm talking about something that is closely related to the curriculum. To begin with, I would like to tell you a proverbial story that most Indians and South Asian folks know. And this is about 6 blind boys or 6 blind monks looking at an elephant or trying to understand what an elephant is. You can see that the first one is touching the ear, the second one is touching the trunk, the third one the tusk, the fourth one the leg, the fifth one the belly, whereas the sixth one is touching the tail. Of course, they give different feedback about how an elephant looks like. And the real elephant, of course, is a combination of the observations made by the 6 blind boys or blind monks. This incidentally is a picture from a temple, apparently from someplace in Thailand, but there are many Indian versions of this story as well. So in a sense, a reaction mechanism is like the elephant, because we cannot see molecules reacting. We cannot see one molecule going to another one in the time scale and in the size that we would like to see it for. And therefore, we use different types of techniques, different methodologies, such as stereochemical and conformational analysis, such as chemical kinetics, kinetic isotope effects, Hammett analysis, and so on, to try to get different components in our understanding of the reaction mechanisms. And when we put things together, then perhaps something close to the reaction mechanism emerges. So I would like to tell you this little story about some fundamental reactions for which the reaction mechanisms were established for the first time in the 1930s and 40s and subsequently. So today my focus will largely be on kinetics, and I would like to tell the audience that there will be some equations, but they will all be very simple. There may not be too much of organic chemistry today, but what I will cover today is basically the principles of application of physical organic chemistry to understanding problems in organic chemistry itself. Before I begin, I would like to set the stage right by telling you about Occam's razor. This is ascribed to William of Ockham, and the Occam's razor principle says that all things being equal, the simplest solution tends to be the best one. There are some modifications of it, particularly when students make fun of their professor in this PhD comics website. There is some description of an Occam's professor who wants the student to do things in the most complicated manner possible. But time to time, I will bring up this issue of Occam's razor when we talk about reaction mechanisms. I have a textbook, I'm sure many of you have read it, by Barry Carpenter, called Determination of Organic Reaction Mechanisms, same as the title of my talk. This was published, more than 25 years ago, but I believe that this is a very nice book to understand a broad view of organic reaction mechanisms. So I will spend a couple of slides on it to talk about the philosophy of how one moves forward in doing experimental research. And these statements I have taken directly from Carpenter's textbook. So the first point is that one formulates a hypothesis to fit the known facts, then design and execute an experiment to test the hypothesis, And the third point is that if the experimental results are consistent with the hypothesis within, of course, the limits of experimental error, one goes to step 4, otherwise goes back and creates a different hypothesis, that is, goes back to step 1. And finally, if all the testable features of the hypothesis have been subjected to experimental scrutiny, then one stops, then the project is complete, or the student leaves, or the grant runs out. And if such things do not happen, then you go to step 2 and again do more experiments. So what you will see today is basically in the context of understanding SN1 reactions, there have been several cycles through this loop between points 2 and 4, and that led to refinements in the hypothesis and refinements of how the reaction might proceed. But a corollary of this is that one can never get closer to the truth than one's own guess, because the hypothesis that I'm going to set up is based on what I can guess based on the known facts. And secondly, you can never prove a mechanism. You can only disprove it. And this is something that the students and the teachers must appreciate. I will spend one slide about hypothesis. And the hypothesis that you are going to set up beforehand, before executing the research, must be consistent with all the available experimental data. It can be neutral about some facts, but should not be in direct conflict with any, unless there is very good independent evidence to suggest that the data that you are going to discard are actually faulty data. And number 2 is very important, that when you set up a hypothesis, you must be able to make experimentally testable predictions, which would, if not verified, be capable of proving it false. Okay, and therefore, the experiments that you are going to use to test your hypothesis should not always be designed in a way that it will support your hypothesis. You should also find experiments that should be able to prove it false. And if it doesn't prove it false, that provides additional support to your hypothesis. And finally, in the event that several hypotheses are found to fit the facts, you give preference to the simplest one. And that is the principle of Occam's razor. And this is probably the last one, that whenever possible, ad hoc additions to the hypothesis as ways to explain our inconsistencies with experimental facts must be avoided. So you don't try to fix the hypothesis by making some ad hoc additions to explain some uncomfortable results. All right, the reaction mechanism, the way the students are taught, usually would start with an arrow pushing. And I did a little bit of research to find out when did this arrow pushing start. And this morning I found that the first 2 examples of arrow pushing in literature were in the same issue of the journal, in fact, JNCASR. The first one was by Lapworth, where he has indicated, this arrow indicating and stated that the curved arrows indicate the direction of movement of the partial valences to or from the bond A0, A1. I think they were talking about butadiene. The second one in the same journal is from Kermark and Robert Robinson. He talks about this, he makes this statement with these 2 arrows as I have shown. Similarly, the conjugation of 3 double bonds, supposing such to occur, would be represented thus. So it indicates this arrow pushing as a way to understand the conjugation. And subsequently Ingold, C.K. Ingold, also used this arrow pushing method, but apparently there were some conflicts between Robinson and Ingold in terms of who first started this. All right. So the 2 types of reactions that students study right from high school are SN1 and SN2 reactions, and everybody knows that an SN2 reaction goes through a single transition state as indicated here, and we are all very comfortable in writing the SN1 reaction profile, energy profile, as shown on the right hand side. And needless to say, that this x-axis, which is typically written as reaction coordinate or progress of the reaction, is something that is kept a bit undefined. I would like to point out to you that the image on the left-hand side is basically a three-dimensional plot. And the three-dimensional plot, what I'm showing here is an atom exchange reaction, something that the physical chemists study have studied in great detail. This is basically H plus H2 giving H2 plus H, an identity reaction in which the energy surface, the y-axis, the z-axis is energy, whereas the x and y-axis are AB and RBC are the distances between atoms A and B or B and C. So you start with a bond between B and C, break it, make some sort of a transition state, and then go to A and B. So the profile that we are drawing on the top is basically a slice of this three-dimensional surface along the orange line that I have shown here, where the transition state is basically the lowest point or the saddle point along the minimum energy pathway. If we look at the SN2 reaction in a different perspective, then the plot may look like this from the point of view of an organic reaction, where we start with an alkyl halide and a nucleophile at that corner, the far back corner. This is the product on the diagonal, whereas on the left-hand side, the front left-hand side, we have a bond dissociation, whereas along the back axis, the x-axis, which is on the back side, it is basically formation of a pentagonal system, a trigonal bipyramid, which of course we know cannot happen with carbon. So for an SN2 reactions, it's a single-step reaction. The bond cleavage along this direction, bond formation along this direction, they take place simultaneously, leading to the path of the reaction coordinate along the diagonal of this squarish diagram. And of course, you can see that as I move my arrow, the cursor along the top, it is the transition state that is located. Let me see if I can mark it here, right here. And this slice of this particular segment is basically the drawing that we frequently make in a two-dimensional representation. I'm not very good in using my tablet, so please bear with me for these poor drawings to some extent. For an SN1 reaction, which is a two-step reaction, it's a first order in alkyl halide and zero order in nucleophile. The diagram looks a bit different. These two images that I'm showing you are from the textbook by Laudy and Richardson. And in this case, the bond breaking takes place first, leading to the formation of this relatively stable carbocation. And in the second bond formation step, which is of a lower energy pathway, you get to the product. So the two-dimensional diagram that we draw here is basically a combination of a slice comprising of this segment and this segment put together, and the reaction coordinate is basically a combination of this line and this line. So you have bond breakage along this direction, bond formation along this direction, and they are happening at different in different stages, and that's why the reaction is two steps. All right. I'm sorry, the stereochemistry and reaction mechanism, this is a wrong title here. We can also take a look at this diagram from the top, disregarding the energy component. And these sort of diagrams are called Jenks, more of Farrell diagram, where we do not talk about the energy, we only indicate the path. So here are the reactants, here are the products. So as I mentioned earlier, the diagonal, which is shown in cyan, magenta, is the SN2 reaction pathway, whereas an ideal SN2 reaction, ideal SN1 is along the red line and the blue line along this side where you form the free carbocation, and then so bond cleavage followed by bond formation. All right, but life is not always so simple, and we will see how things get complicated. But first I would like to develop a little bit about the kinetic parameters, how you plot the data and how you can interpret mechanism from a given kinetic expression. So this, I think everybody knows, this is for a first order reaction where the concentration changes exponentially depending upon the rate constant K. And in order to establish the value of K, in order to measure the value of K, what you need to do is to plot the initial concentration versus the concentration of the reactant at time T, and you get a straight line which has a slope of K. So that's very easy to get a first order plot if the reaction is completely first order. And that's what one would expect in an ideal SN1 reaction. Whereas for an for a reaction where it is 2 steps, but the second step, but the first step has a reversibility, then one can analyze the overall kinetics using the so-called steady state approximation. This is also something that is very well known to the students. And this condition is fulfilled provided K minus 1, that is this step, is much, much larger than K1, or K2 is much, much larger than K1, indicating that B is basically present. The rate of change of the concentration of B is very, very small. In that case, one can apply the steady state approximation and then get to an equation which looks like this. And I will come back to this issue a little bit later. Now, when you have a given mechanism, for example, like this, and you apply the steady state approximation, you can develop the equation. But then suppose we ask the reverse questions. Suppose I measure the rate of a reaction and it follows a certain kinetic expression. Can I infer something about the reaction mechanism? Unfortunately, this is not completely correct. For instance, a given reaction mechanism always defines a unique rate law, but a given rate law does not uniquely define a mechanism. But still, some general conclusions may be drawn from the analysis of an observed rate equation. And I would like to use the next couple of slides to highlight such possibilities. The first one is that if you have a single step reaction, and I'm giving a very arbitrary and somewhat abstract rate expression where the rate is K times A concentration raised to the power A, B to the power B, C to the power C. This basically implies that you are going through a transition state whose chemical composition is A times A plus B times B plus C times C. Rate law looks like this if it has a summation having 2 different parameters, 2 sets of concentrations. That implies the existence of 2 parallel reaction pathways, and it leading to and will lead to transition states whose compositions are A plus B in one pathway, A plus B plus C in the other pathway. Now, this only tells you the composition of the transition state. It doesn't say anything about the structure. That's something that should be remembered clearly. One more point I would like to indicate to you is that if there is a sum in the denominator in your experimental rate equation, that implies that the reaction goes through at least 2 steps, or in other words, it has at least one intermediate that is formed reversibly. And if there are 2 steps, then obviously there are 2 transition states. And you can find out the composition of the transition state. Once again, I would like to remind that it is a composition, not the structure, by making one term or the other in the denominator to be the dominant factor. For example, if I make K prime times A much, much greater than 1, then I'll be left with B squared. That means I have a transition state whose chemical composition is 2B. If on the other hand, 1 is much, much greater than this, I have A and 2B in the numerator, which means the second transition state has a chemical composition of A plus 2B. And that sometimes can allow you to distinguish between 2 possible reaction mechanisms. All right. So after setting the stage right, let us take a quick look at SN2 reaction. I will not spend too much time on SN2 reactions except on my very last slide. And in this case, the rate expression is very straightforward. If it is second order, it's a second order reaction, first order in nucleophile, first order in alkyl halide, except if the nucleophile, for example, the solvent is present in large excess, then Ka2 times nucleophile is a constant. In that case, the reaction essentially becomes a pseudo first order reaction. On the other hand, as we discussed earlier, for an SN1 reaction, typically the bond dissociation is believed to be slow whereas the bond formation with the nucleophile is believed to be fast, and therefore K1 is the rate determining step. And as we know that whatever happens after the slowest step would not appear in the kinetic parameter, and therefore rate is a first order reaction, K1 first order in Rx. Now there's a problem here. The problem is that in most cases when R plus is formed, imagine that you are a carbocation and you have the nucleophile around, which is typically a neutral nucleophile. And you also have X minus, an anionic species that is being formed as a function of time. Now you would now have a choice of going forward with a neutral nucleophile or going backward in the same step to regenerate the alkyl halide. In other words, particularly when X minus happens to be a good nucleophile, you must have the option of including reversibility in the first step. Now that makes life more complicated. And what happens is that now we have to apply the steady state principle, steady state approximation to R plus. And if you do that, you end up with an equation like this. I will not derive the equation, but this is again very standard based on what I showed already. In this case, you get an equation with X minus appearing in the denominator. Okay. And of course, if the solvent, that is R-OH, is present in a high concentration, you can combine these two, make a composite rate constant, pseudo first order rate constant K2 dash, and your reaction kinetics looks simpler. Okay, but nevertheless, you have X minus in the denominator. Now, what does it suggest? That suggests to you that if you are carrying out an SN1 reaction where the first step has some reversibility, then the first order plot, that is the plot typically where you plot Rx0 by Rx, ln versus T, it should show a downward curvature. Why? Because with time, this concentration will increase and therefore the denominator will start to increase and will reduce the actual value of the numerator. Not only that, if you add X minus from an external source, the rate will reduce, which is commonly called a common ion rate depression. All right. So these are two testable predictions from the hypothesis that you can have reversibility in the first step. Now, these studies were initiated, as I told you, in 1940 by Ingold. And what he did, he looked at the solvolysis of dimethyl benzhydryl chloride and plotted ln C0 by C versus T. And sure enough, the plot showed downward curvature. And in the presence of added lithium chloride, the rate got depressed. And you notice that there is no curvature here because you are adding so much of lithium chloride that the halide ion concentration is more or less constant. So the amount of chloride added from RCl is actually small compared to lithium chloride. So therefore, the line becomes linear, but the curvature but the slope is lower than what you see with RCl. So that means that everything is right. The hypothesis is fine, and the testable predictions are all observed. So do you stop doing research? Well, Ingold chose to try it out with a few other substrates. Okay, this is what happens when you go through this 1, 2, 3, 4, 1, 2, 3, and go back to step 1 or step 2 and try out more experiments. And when he did the second experiment by simply removing the 2 methyl groups, things did not look particularly similar to this. In this case, there was very little observed curvature in the first order plot, and added lithium chloride did not seem to change the rate very much. And then you do one more experiment with tertiary butyl bromide. Okay, now that puts your hypothesis at risk, because what you observe here is that there's an upward curvature, and added lithium bromide, which was supposed to have a common ion effect and reduce the rate, as you see here, in fact, it increased the rate. Okay, so the question is, what's going on? What's going on was understood, some idea about it came when Ingold and team added lithium bromide to the first reaction. In that case, the rate in fact went up. So he came to the conclusion that there are two effects here. One is that in such cases, in butyl bromide, there's a salt effect rate enhancement, whereas in the case of dimethyl benzhydryl chloride, there is common ion rate depression. And then the question was why these two are behaving in two different ways. Now, first we will take a look at the salt effect rate enhancement. It was known at that time, 1940s, that if you carry out an SN1 reaction in the presence of salt in an aqueous system, adding salt essentially increases in a simpler way the ionizing power of the solvent. So the rate constant K1 is sort of a linear function of the ionic strength or the concentration of the ionic species, because K1 gets enhanced, that is, the dissociation gets enhanced in the presence of a salt. So increased ionic strength increases the propensity of RX to dissociate. And empirically, it was found that normal salt effect is basically linear dependence of the rate constant with the ionic concentration. And then the equation is something like this. K1 increases linearly with the X minus concentration. And now if we put this in the second order, in this expression where we had a denominator term, we see now that after the addition of this in place of K1, there is X minus in the numerator and X minus in the denominator. Okay, and therefore added X minus can affect the rate in somewhat unpredictable way. So what INGOLD did was to look at two extreme possibilities. Possibility one, where the first term in the denominator is dominant, and possibility two, where the second term is dominant. So let's say in case one, let us make K minus 1 X minus to be the dominant figure. So we remove this parameter, we remove this from the equation, and then the equation gets reduced to something like this. Excuse me, I think we have to remove this because the other term is dominant, right? So we remove this one first in case one. So this is the dominant term. And when we simplify this equation, we find that X minus is present in the denominator, indicating that in such situations, we will have common ion rate depression. In that case, of course, we will have added X minus causing a reduction in the rate and causing a downward curvature. In case two, when we set that this is the dominant term, then we remove the first term here, and then you find that I have X minus only in the numerator, indicating that in this case, the added X minus will increase the rate and cause an upward curvature, leading to salt effect rate enhancement. Now, this is all mathematical manipulations trying to understand your observed results. Let me go back and take a look at it again. So the point is that in this case, we saw common ion rate depression. In this case, we saw salt effect rate enhancement. What does it tell us about the structures? So this is something that I have already mentioned. In the first case, when we say that in this case, K minus 1 X minus is much, much greater than K2 times R dash OH, that would imply that this inequality, that is K minus 1, should be much, much greater than K2. Okay, therefore, for the first case, we would infer that K minus 1 is much, much greater than K2. All right. And in the second case, case 2, if this term is much, much, would imply that K minus 1 and K2 are comparable. Because, you know, K minus 1 is the rate of reaction of the carbocation with an anionic nucleophile. K2 is the reaction with a neutral nucleophile. And by experience, a neutral nucleophile is always worse than an anionic nucleophile. So this inequality essentially implies that K minus 1 should be comparable to K2. Now, again, we need to understand what these things refer to in terms of the two sets of reactions. Now, in this case, what was believed is that you are going through a carbocation which is very reactive. A very reactive carbocation, remember that this is the K minus 1 step, whereas this is the K2 step. Okay. Now, if it is a very reactive carbocation, it will be very non-selective. There is something called a reactivity selectivity principle, which is not always followed. But in this case, if we apply that and say that the T-butyl carbocation is a reactive carbocation, and therefore it does not discriminate between an anionic and neutral nucleophile, then this condition might be satisfied and we will get a salt effect rate enhancement as we observe here. On the other hand, for this case, where we get a more stable carbocation, if the carbocation is more stable, then it will be able to discriminate between an anionic and a neutral nucleophile, and therefore this inequality may be established and we will see a common ion rate depression. Okay, and therefore what these results indicated is basically that if you have a stable carbocation, you get salt effect, you get common ion rate depression. And if you have a unstable or a reactive carbocation, then you get a salt effect rate enhancement. And clearly, compared to T-butyl cation, the doubly benzylic benzhydryl cation is more stable. Whereas in the second case, remember, we didn't speak about the second case. In the second case, there is X minus in the numerator, there is X minus in the denominator, and therefore these two kind of balance things out, and therefore the rate seems to be invariant to the addition of an external common ion. All right. So in this particular case, we have some product character. Okay, let's not go into all those details now. So this represented a reasonable understanding until Winstein started studies in 1951. And what he did, I will go a little faster now because my time is kind of less. So what he did is to look at the solvolysis of these two allelic halides, the primary and the tertiary halide, in buffered acetic acid. And the reason he used buffered acetic acid, because acetic acid is a good nucleophile and will prevent the reverse reaction, that is the K-1 step, because it will only, once the cation is formed, acetate will trap it faster than chloride, because under the conditions of the experiment, acetate is a better nucleophile. So what he did is to start plotting the acetate ion concentration. The reaction was monitored by measuring acetate ion. You know, these are the old days when sophisticated techniques for measuring kinetics was not available. So people would do titrations to measure reaction rates. So as expected, there was no common ion rate depression. You know, that is a very important point to remember. Now, as far as the primary halide is concerned, the first order plot showed a linear plot. But there was a bit of surprise when they looked at the other molecule, that is the isomer, tertiary isomer. It initially showed a very steep increase in the reaction rate, and then it leveled off and followed a slope similar to that observed for the primary halide. And then the question is, what's going on? So what Winstein and team did was to analyze the reaction mixture around this time. Okay, and what they found, interestingly, is that B got isomerized to A around this time. All right. So what, therefore, it implied is that initially B undergoes solvolysis at a faster rate compared to A, but it also undergoes isomerization to A. And when all of it got converted into A, it starts to solvolyze with a rate identical to that of A. So that was understood. The kinetics was understood, but then the question is, how on earth A gets isomerized to B? All right, and it cannot be because of a 1-3 shift. Of course, at that time, you know, all these Woodward-Hoffman rules were not known. We are talking about 1950. And another reason was that this shift took place only in very polar solvents, not in non-polar solvents. Because if it is just an intramolecular shift, it should happen in a non-polar medium. That did not happen. And then because there was no common ion rate depression observed, that implied that it was not going through a free carbocation, all right? Because it is not going through a free carbocation and the recombination, because there was no common ion rate depression observed. So at that time, to put together all the observations, what they proposed is that the reaction is not as simple with the reversibility in the first step, but there must be a second step involved in which you generate a contact ion pair or an intimate ion pair. Ion pairs were known in inorganic molecules, which were initially indicated by concentration-dependent conductivity measurements, but this was the first time that the existence of ion pair in an organic transformation was first proposed and evidence was presented. So basically what it means is that you need to dissociate the ion a little bit, make a contact ion pair, and this can isomerize and go from B to A in that process. If I had said A to B, that's wrong. In the previous slide, it is the tertiary one that isomerizes to the first one and seems to be going through a contact ion pair. Now, when you introduce one more intermediate, then obviously your kinetics gets more complicated. And I have indicated here that remember Occam's razor. And point here is that you should not propose the existence of contact ion pair for every SN1 reaction. Only when it is absolutely required to explain the kinetics or some other experimental observation, you need to propose the contact ion pair's existence. Now, coming back to the multi-step process now, the reaction, the kinetic parameter gets a little more complicated, and the students can derive this equation if you apply steady state approximation to both intermediates, R plus X minus and R plus. And this will be good exercise. It should not take more than, at the most 2 sides of an A4 size sheet of paper. Okay, but some algebraic manipulation may be needed. And I would strongly recommend that all students try it out, all right, to derive this equation. All right, so this is fine. So then, in some cases, we can have the alkyl halide going to a contact ion pair, going to free carbocation, and finally forming the product. And then it turned out that there was a twist on it. Goering and Levy started to look at the reaction, SN1 reaction of this benzhydryl derivative. And you notice here, this molecule is very special because it has got little star here, which is a chiral center or stereogenic center, whereas the leaving group has the 2 oxygens differentiated by one regular oxygen, the other one is an OAT. And if it forms an ion pair and it goes back in the K-1 step, in other words, if this bond is broken in a heterolytic manner, in this manner, then 2 things can happen when they recombine. The chiral center, this center may get racemized, and the 2 oxygens may get exchanged. So there are 2 ways by which, when you analyze the recovered starting material, you're not analyzing the product here. Okay, you are letting the reaction go for a short time, then isolate the unreacted starting material or something that has reacted and come back, and then analyze them by mass spec. All right. In this case, as I said, that it can either undergo racemization or it undergo exchange, and you can measure both the rates independently. So K exchange is a measure of the total ion pair return. That is how the ion pair comes back to the recovered starting material. Whereas the optical activity, if it gets racemized, then K racemization or the rate of racemization is a measure of the racemization associated with its going back to the starting material. All right. And experimentally, K exchange was found to be larger than the rate of racemization by a factor of 2.3. And what it really meant is that the ion pair returns predominantly with retention of configuration because the exchange is faster than the racemization. Because it was understood that a little bit of the formation of the ion pair will be enough to exchange, but not enough to racemize. And that basically is what you see from this data. Now, they did one more reaction. What they did is that they used azide ion to carry out a reaction of the R plus, okay, to sort of divert it from reacting with the neutral nucleophile and reacting with azide, which is a good nucleophile. And then there was a surprise. The surprise is that the exchange I should say K exchange here. Exchange rate remained unaltered, but the racemization became 0. In other words, there was no racemization. And at that time, Goering and Levy were concluded that the highly nucleophilic azide must be intercepting an intermediate that returns with racemization, but not intercepting one that returns with retention of configuration. In other words, in the presence of azide, this cannot be trapped, but there is something else that is getting trapped. Okay, and that something else they proposed is a solvent separated ion pair, often referred to as the acronym SSIP. And that's the time when they proposed that not only do you have an ion pair, but you also have a solvent separated ion pair, because azide traps this intermediate, but not this intermediate. So in the presence of azide, this can go back in the K-1 step and form exchange of the 2 oxygens, but there is no racemization, because for racemization, you need to go to the K2 step and K-2 followed by K-1. All right. So what I basically said is summarized here. The contact ion pair returns to the reactant more rapidly than it is captured by azide, and the solvent separated ion pair is captured by the azide ion faster than it returns to the racemic reactant. I would, this adding this scheme makes the reaction look very, very ugly, and I will not say anything about this. I think I'm also reaching the end of my presentation, and I will also skip the last part, which is basically another philosophical discussion that, when you have contact ion pair and the solvent separated ion pair, do you really need to form the free carbocation? And the answer is yes, because you can show using certain modified expressions that, the fact that you see common ion rate depression or return of the ion back to the reactant implies that there should be free ions, and this is not enough to explain that. All right. But then again, you would like to remember Occam's razor, not every reaction is supposed to go through a contact ion pair or a solvent separated ion pair. So unless the data requires that you have to invoke the existence of contact ion pair or solvent separated ion pair, you do not invoke them. All right. You do not say that these are formed. All right. But something that I would like to point out to you is that as you go from the alkyl halide to the contact ion pair to the solvent separated ion pair to the free cation, what is changing is the hybridization of the carbon, which is represented as R, from sp3 to pure sp2, and the extent of positive charge on the carbon is increasing. Okay, and I will show you in one of my last slides that you can in fact find other techniques by which you can find out whether K1 is rate determining or K2 is rate determining or K3 is rate determining, depending upon how much charge or how much sort of sp2 character you have in the transition state. And one of the ways by which you can do it is for SN1 reactions by looking at the kinetic isotope effects, and I will show just one slide on it. Whereas for SN2 reactions, which are supposed to be concerted reactions, but then I would like to show again with one or maybe two slides that using Hammett equation, which is another tool, another technique for understanding reaction mechanism, you can indicate whether the reaction is synchronous or asynchronous. Here's a quick example of using a secondary the carbon with a brosylate group. I assume that many of you know about kinetic isotope effects. In this case, it is a beta secondary kinetic isotope effect. And when it is solubilized in trifluoroacetic acid, the kinetic isotope effect is relatively large, 1.46. Whereas if it is done in a less ionizing solvent, 70% aqueous trifluoroethanol, it is 1.22. And from which the authors who did the experiment, they suggested that in the first case in trifluoroacetic acid, it is excuse me, I think it's the other way around. It is K2 that is rate determining. These two are exactly the opposite. K2 is the rate determining step. That implies basically that you have more charge in the transition state on this carbon, and that's why the kinetic isotope effect is larger. Whereas in 70% trifluoroethanol, which is less ionizing, it is the first step which is rate determining. The extent of charge on the carbon, on this carbon, is relatively less, and that is why you see lesser value of the kinetic isotope effect. So in other words, K2 is rate determining in the first case, K1 is rate determining in the second case in trifluoroethanol. Let me close my talk with an example of SN2 reaction. Just to sort of set the stage right, I would like to show one slide on Hammett equation. I assume that most of the students have studied Hammett equation, which says that, if you plot the variation of the rate as a function of a substituent X in an aromatic system and compare that with that of the unsubstituted molecule and plot against the substituent parameter sigma, you can get a straight line with either a positive slope or a negative slope. And that implies if rho is positive, then electron withdrawing groups will accelerate the reaction. If rho is negative, electron donating groups accelerate the reaction. Or in other words, electron donating groups will slow down the first reaction. Electron withdrawing groups will slow down the second reaction. And basically what it says is that if rho is greater than 0, if electron withdrawing groups are accelerating the reaction, you have an accumulation of negative charge in the transition state. Whereas if rho is negative, you have an accumulation of positive charge in the transition state. So that's why electron donors accelerate the reaction. Now, again, as I said, life is not always as simple as a slope with a positive value or a slope with a negative value. There are situations where you get a more complex non-linear Hammett plot. And that will be my last slide. And I think I'm still within my time limit, Dr. Ghosh. So this is a reaction. Okay, thank you. This is a reaction in which you are using a super nucleophile, a very good nucleophile, paramethoxy thiolate, benzene thiolate, with this benzyl bromide using and you vary the reaction as a function of X. Now, normally you would expect if bond formation, and let me try to push the arrows now, having talked about arrows since morning, this arrow versus this arrow, if these two are happening at the same time, then this carbon is not going to have any accumulation of positive or negative charge. In that case, there should be no effect of the X group because the bond formation and bond cleavage are taking place at the same time. Anionic nucleophile comes, anionic Levig group departs. There's no net charge change on this carbon. But then again, life is a little bit different than what we can predict. In this case, you get a nonlinear Hammett plot. It's just a schematic diagram to indicate that both electron withdrawing groups and electron donating groups are accelerating the reaction. Okay, how is that possible? So in this case, what was predicted is that, well, it's an SN1 reaction, all right, but the part in which electron donating groups on the aromatic ring, okay, are accelerating the reaction implies that this bromide group is leaving slightly ahead of approach of the nucleophile. Okay, so basically the electron donating group is kicking out the bromide before the nucleophile can come, and therefore there's a net accumulation of positive charge and therefore a negative value of rho. On the other hand, for the second set of reaction, that is with electron withdrawing groups, you know, the leaving group bromide cannot leave so easily. So the sulfur is attacking before the bromide starts to leave. And that leads to an accumulation. You know, you're not forming a trigonal bipyramid. You're not forming a pentavalent carbon. But in the transition state, the bond formation and bond breakage are asynchronous. And that essentially implies that for the yellow part, we have bond cleavage going ahead of bond formation. Whereas for the green side, we have bond formation occurring asynchronously, slightly ahead of bond cleavage. And therefore, this magenta line gets shifted slightly towards this side or slightly towards that side, depending upon whether you have an electron donating group or an electron attracting group. So these are very subtle changes in the reaction mechanism that you can infer in appropriate cases by the study of Hammett type correlation. I think my time is getting up, so I should close now. But I would again like to come back to this picture of the elephant and say that the reaction mechanism is a very complex situation of molecules of the size of nano-sized objects and sub-nano-sized objects moving from one form to another one with an extremely high rate, and we cannot see them, at least in more complex organic molecules. For simple cases, yes, with fast laser techniques, you can get some inference about how things are happening. But for most organic reactions, which are much more complicated to be studied in such detail, we have to resort to indirect methods like stereochemical conformational analysis, kinetics, kinetic isotope effect, Hammett equation, and combine all of them to eventually get some idea about the elephant, which we cannot see. So with this, I would like to conclude my talk. I would like to thank again Professor George, Professor Rao for initiating this excellent FCBS workshop, which I had enjoyed participating every single year. And I would also like to thank the NIIST and IISER Trivandrum administration and the colleagues for putting together this very nice online platform for this for the event starting today. Thank you very much.
Okay, thank you, Professor Uday Maitra, for this excellent lecture. In fact, I forgot to tell you that, use 45 minutes for your lecture and leave 15 minutes for discussion.
Oops,
So,
I am sorry, I have used more time.
yeah, so maybe we can take one or two questions if the audience or the students, they have anything to ask. You can either raise your hand or you can put it in the chat box. Please quickly do it because we are running short of time.
Yeah, I had my clock on, but then I guess that I started a bit late. So anyway, yeah, I'll be happy to answer questions. If you don't have questions immediately, you can send it to me by email.
Yeah, that is also possible.
More than happy to answer that, as we used to do in the last session in the FCBS workshop. Some
but
questions.
If anyone would like to ask any quick question, you can raise your hand. Anybody? Okay, if there are no questions, I take this opportunity in thanking Professor Uday Maitra for this wonderful talk. I'm sure the students community, it's extremely useful for them to learn some of these important topics in organic chemistry, especially physical organic chemistry. And but as already said, if you have any doubts or anything to clear, please be in touch with Professor Uday Maitra. He will be happy to entertain your question. Okay, with this, Joshi, Raji, and all, shall we move to the next one?
Yes, sir.
Okay, so the next talk is given by Professor Ishara Murthy. Again, Professor Ishara Murthy very well. He he participated in most of our FCBS meetings. He has earlier given lectures in this forum. Professor Ishara Murthy is a faculty at Jawaharlal Nehru Center for Advanced Scientific Research at Bangalore. And he is known for his work in the field of nanomaterials, catalysis, and porous materials, covalent organic framework, metal organic framework, clay composites, etc. So today, Professor Murthy will be, Ishara Murthy will be talking to us on green chemistry and catalysis. Professor Ishara Murthy,
Yeah. So
I'm requesting you to take 45 minutes.
Yeah, alert me
talk
some
so that we'll have some time for discussion.
Sure, alert me some 5-10 minutes before.
Yeah.
Thank you. I can switch on this one video and then go for share. So able to see the screen?
Yeah, you can go to the presentation mode.
Yeah.
Yes, fine.
Something still coming inside. Yeah. Thank you, Professor. It's something is reflecting. It's echoing something. Hello. Ajay, I'm hearing my voice.
Yeah, we can hear you.
No,
We
no,
can hear your
it is
slide. Please
reflecting.
proceed.
My voice is echoing.
Is it okay now, Professor Isharamurthy?
Yeah, yeah, now, but still it's coming in. Is that clear now?
Yeah. It's very clear to us.
Okay. So thank you, Professor. Oh, no, it is coming back. Hello.
Are you, Dr. Isharamurthy, are you using headphone?
Yes. Shall I remove?
Probably you can. Yeah, you can try removing and.
So is that clear now?
For us, it is
Yeah,
clear.
for us, it is okay. No problem.
Is that clear now?
Yeah.
Okay. I will try. If it is going, I will remove that. Thank you, Professor Ajay Ghosh, for the nice introduction. So at the outset, I would like to thank Professor Rao and Professor George for conceptualizing this wonderful event every year, which is very useful for many students and teachers across the state of Kerala. It is a sad moment. It's a sad feeling to realize that Professor George is not with us today. His warmth and affections, whenever we see him, is still lingering on our mind. So with this, I start my talk, the green chemistry and catalysis, which I am going to talk. Reggie, still I am getting the same problem.
Oh, really?
Yeah.
We have all of us muted.
Is that?
There is no one, no participant is unmuted
Yeah.
except you and now me.
Okay.
Isharamurthy, make sure that there is no other device close to your, your computer,
It is not
which is, or have you logged in through 2 devices at the same time?
No, that I came out.
Okay. So
But
log in only through one device and also remove any other devices which are very close to your computer.
Yeah, I removed it.
For all of us, I think the audio and video are very clear.
Okay. Maybe I am only getting this one reflection. I'll just go remove my this. Okay. So to start with, now can you hear me?
Yes, we can hear you, and your presentation is now in the edit mode. You can go to the PowerPoint mode. Presentation.
Hello. Sorry for this. So reasonable working definition for chemistry. So green chemistry is efficiently utilizes raw materials, eliminates waste, and avoid the use of toxic and hazardous reagents and solvents in the manufacture and application of chemical products. Make it slides. So there are 12 principles of green chemistry. 1, waste prevention instead of remediation. 2, atom efficiency. Hello?
Yeah, we can hear you.
Okay, fine. Okay. So the 3, less hazardous and toxic chemicals, safer products by design, innocuous solvents and auxiliaries, energy efficient by design. So these are the 12 principles of green chemistry. So the catalysis contributes to the green chemistry in many ways. One, to reduce or remove the solvents used, reduce the reaction temperature, reduce the purification steps, or improve the selectivity and atom efficiency, and replace with the renewable raw materials and remove the pollutants. So these are the many ways that catalysis can contribute to that green chemistry. So as per Martin Polyakov, catalysis is one of the central tools for the greening of chemistry. Catalysis not only can improve the selectivity of a reaction, but also by doing so, it can decrease or even remove the need for downstream processing, thereby reducing the material and energy waste associated with the purification. This is particularly important because the solvent requirements for crystallization, chromatography, and other purification processes are often much greater than the usage of solvent in the original reaction. And catalysis is not just a new one, it is not a new terminology. Many catalysis processes were used a long time ago, many decades ago, to produce valuable chemicals. So one such catalysis reaction here, conversion of starch to sugar by Kirchhoff's in long 1780s or something. So he used acid catalyzed reaction. So this produces glucose, and he is also a person who developed that method for refining vegetable oil. In fact, he established a factory that prepared 2 tons of refined oil every year. And this another important person, Humphrey Davy, who first shows evidence that a chemical reaction between two gaseous reactions can occur on a metal surface without the metal physically changed. Or even chemically, it won't undergo anything. So when I was accidentally led to the knowledge of the fact that oxygen and coal gas in contact with the hot wire combined without flame and yet produced enough heat to preserve the wire ignited. I have tried various metals, but succeeded only with platinum and palladium. With the copper, silver, iron, gold, and zinc, the effect is not produced. So this is what Davy noted in his experimental book. He suggested that this could be used to build a non-explosive lamp for mining operations. And this was that Davy's lamp. To stop. Yeah. So this is a Davy lamp, which saved thousands of miners. In those days, they get kind of fire accidents in the mining, coal mines. And he is the one who discovered laughing gas. He discovered sodium and potassium, the electrochemical reactions. He was a pioneer for many electrochemical reactions, to say that. And this is that Dauberner, who showed that the manganese dioxide can catalyze the decomposition of hydrogen peroxide into oxygen and water. And he also showed that to generate that kind of fire by creation of the hydrogen from the addition of sulfuric acid to zinc, which in presence of platinum forms that ignites and that leads to the fire. So very important on the fire on demand, he used a platinum sponge as a catalyst. So his fire lighter demonstration in 1823 caused a sensation, and thousands were sold across Europe until superseded by the phosphorus match. In fact, it was developed by one of his students, Rudolf Bodger. So Dauberner never profited from his inventions, but he wrote, "I love science more than money, and the knowledge that I have been of use to many mechanical artisans makes me happy." In fact, he was buried with no coffin. 2 fruit trees planted above his grave to benefit from the decomposition of his body. So there are the old days catalysis, and in fact, later that it is still used for many reactions. Classical aromatic chemistry in the manufacture of organic compounds. You can see the stoichiometric amount of metals used for the reduction reaction and stoichiometric amount of potassium permanganate, dichromate. They were used for the oxidation reactions, and even mineral acids, nitric acid, hydrofluoric acid, and phosphoric acid were used for sulfonation, nitration, and other reactions. So this kind of classical aromatic chemistry generates a huge amount of inorganic waste. And later that non-classical aromatic chemistry, they used the hydrogen, oxygen, or hydrogen peroxide as the direct source for hydrogen, oxygen, and carbon functionalization. And they use recyclable solid acids or bases like zeolites as a catalyst. So they can circumvent the formation of huge waste. So there are two important things one has to look at it in the catalysis: the atom efficiency and the E factor. So atom efficiency, the molecular weight of the product divided by the sum of the total molecular weight of all the substances in the stoichiometric equation. So here, for example, the 1-phenyl ethanol undergoes oxidations with the atom efficiency of only 42%. Whereas in presence of molecular oxygen in catalyst, with the catalyst, it gives that atom efficiency of 87%. So the huge change in that atom efficiency, almost 100% increase. There is another important factor, E factor. It's nothing but how much kilogram of waste produced per kilogram of product. See, for example, in this case, a diphenyl methanol to benzophenone reaction, when you use the stoichiometric reagents of this chromium oxide and then hydrogen sulfuric acid, so nearly 1 kilogram of waste for every kilogram of product is produced. It's a huge amount. And also another reaction, fluoroglucinol from TNT. And this again is also used as a medicine. And here, if you look at these steps, that atom efficiency through these reaction steps gives you the E factor, the 5%, less than 5%, and the E factor is 40. So that means it generates 40 kilogram of solid waste for every kilogram of fluoroglucinol produced. It has to be placed in a museum of industrial archaeology. So if you look at the many industrial segments, the oil refining industry, they produce nearly 1 million tons of the products, where the waste produced is a 0.1 kilogram per kilogram of product. In bulk chemicals, they are again 10 power 4 to 10 power 6 tons of products, where the wastage is 1 to 5 kilogram waste per kilogram of product. More importantly, in pharmaceuticals, where thousands of tons produced, the waste is around 25 to 100 kilogram per kilogram of product. So few examples I'm giving here. For toluene oxidation to benzoic acid, the conventional or classical route is the chlorination followed by hydrolysis, where the atom utilization is around 36%. Or even a nitric acid oxidation, the atom utilization is 56%. So later, using molecular oxygen and the catalyst, where the solid catalyst, where the atom utilization comes around 87%. It's a high atom utilization, and also no chloro or nitro products, oxygen being a cheap oxidant. And even the Fidelkraft's reactions in a classical route, for example, in these reactions, you can see 4.5 kilogram of waste per kilogram of this product. This acetylation reaction, well-known Fidelkraft's reaction. And when you use with the beta catalyst, zeolites, you can reduce this waste to 0.035 kilogram per kilogram of product. Even the caprolactam synthesis, a conventional route gives a 4.5 kilogram of waste per kilogram of product, whereas Sumitomo process, where the hydrogen peroxide generated from hydrogen and oxygen combination with ammonia in presence of titanium silicate zeolite or molecular sieve gives you a 98% caprolactam with very high atom efficiency. And even the production of ethyl acetate, the conventional route acetic acid esterification or acetaldehyde condensation. In fact, almost 1990 to 2001, they used this process, and later they have introduced the British Petroleum and Avada process. So it was 2001 installed. The production almost 2.2 million tons per annum. Nothing, it's just simple ethylene plus acetic acid gives ethyl acetate. 100% atom efficiency. The catalyst used the heteropolyl acid and silica support, where they won the AstraZeneca award for green chemistry and engineering. The another reaction is a catalytic dehydrogenation of ethyl benzene to styrene. In fact, styrene demand is 25 million metric tons to make polystyrene in the industry. It's an endothermic reaction. So high conversion happens only at high temperature and low pressure. So it has to operate at less than 70% conversion to get good selectivity. There is a smart process, styrene monomer advanced reheat technology, the process introduced by ABB, Lummus and UOP in 1995. So it's an endothermic process. They used very cleverly that burning hydrogen in presence of oxygen to get the heat generation, which again drives this reaction. So they use oxidation of hydrogen, shifts the equilibrium. So greater than 80% even at low feedstock. So the productivity increased by 50%. It's a very important industrially renowned process. This is not moving. Yeah. So this is another classical process to produce ibuprofen. Here the multi-step process, atom efficiency leads to 40%. There's a Boots-Host cleans route to ibuprofen. This reaction is BHC process introduced by BASF in 1992. In fact, it's almost 35,000 tons produced per annum. So the atom efficiency is almost 77%. Almost waste-free synthesis eliminates large volume of salt waste, but still the HF and acetic acid are recovered and recycled with 19.9% efficiency. And they also got that Kirkpatrick Achievement Award for Outstanding Advances in Chemical Engineering 1993, and also US Presidential Green Chemistry Award 1997. So it's a very important process again. Another one, Mitsubishi Rayon process for production of acrylamide. So now they are producing nearly 100,000 tons per annum in a very nitrile hydratase enzyme reaction using wholesale. So that produces acrylamide from acrylonitrile. Earlier, the people used a Rani copper catalyst, where the conversion is only 50%, though its selectivity 100%. But again, leaching of copper is a big problem. So that was that process replaced with this Rayon process. This is a paclitaxel process, BMS paclitaxel process. This paclitaxel is one of the medicine used for cancer patient treatment. Earlier days, it was isolated from bark of Pacific yew tree. This is one of the slowest growing trees in the world. To treat one patient, you require cutting down 600-year-old trees because the bark contains less than 5 ppm paclitaxel. In 1994, the total synthesis by Nicola and Robert Colton group, the 40-step synthesis, gave 2% yield. Later, they identified the 10 DAP, that another important precursor for this production of paclitaxel, the isolated from European yew tree leaves. So here you need not cut the trees. So without harming the tree, you can extract the 10 DAP. From that, you can bring the paclitaxel. So in 1998, the Taxol became one of the world's most profitable trucks. It was sold 1.5 billion euros per annum. So later the fermentation method introduced, and then they got a Green Chemistry Award in 2004. So another important catalyst which play a major role in the green process is zeolites in industry. This is nothing but aluminosilicate. You can see that silica tetrahedra and aluminum tetrahedra, whereas silica is linked with the 4 oxygen atom. So the Si4 plus is a neutralus. And here the Al3 plus, it carries one negative charge because the 4 oxygen atom. So this negative charge is compensated by the sodium cation or calcium cation. So this one can be used as an acid catalyst by replacing the Na plus with the proton H plus. So you can replace by treating with ammonium nitrate and calcination, you will get with the H plus form. So this can be again used for many catalytic reactions like superacids. So almost many petrochemical industries where zeolites are used for cracking nowadays. And today, most of the energy needed to drive your car comes from crude oil, a complex mixture of hydrocarbons, which includes long chain alkenes and aromatic hydrocarbons. So it has to undergo reforming and cracking reaction to get a linear alkenes, and this again converted into branched or cyclic versions. So the breaking up of heavier hydrocarbons to lighter ones carried out by this kind of solid catalyst zeolites. So in fact, this has another added advantage because of the shape selectivity. So these pores are almost like a molecular size. So many reactions can happen if the reactant molecule, if they get into that pores. For example, if you have that one linear chain and branched chain, so out of this, only the linear molecule can get into the pores of the zeolites, where it can undergo the cracking, whereas the branched one cannot get into that. So the reactant selectivity you can see here. So in the mixer, you can selectively crack one particular reactant. And there's a product selectivity. In case of toluene alkylation, if the reaction happens inside the pores, you will selectively get that paraxylene compared to the meta and orthoxylene. So this is a product shape selectivity. So it all minimizes all the industrial separation, purification of these mixers. You selectively get the paraxylene, which is used for an textile industry as a raw material. And also there is a transition state selectivity where it controls the reaction inside, a transition state of this product inside, and then get one particular product. So this is a very important catalyst and billions of dollar business involved in this. And earlier was the Howry process. The catalytic cracking is used by the clay, the fuller's earth. Howry is a mechanical engineer and an automobile racing driver looking for good gasoline to speed the car. So he found that the clay, which can crack those crude kind of the oil, long chain hydrocarbons into small, which can be utilized for this fuel. Thereby he can drive the car very fast way and win the race. So the Howry catalytic cracking, introduced by Howry in 1936, first commercial continuous process. So the reactors fixed with natural alumina silica pellets used as a catalyst. And he started a Sun company, refinery of Sun company. So during the World War II, the high octane fuel shipped from the Howry plants played a critical role in the Allied victory against Germany. In fact, Winston Churchill, he made the points, never in the field of human conflict has so much been owed by so many to so few. So his famous tribute to that RAF's victory in the Battle of Britain, owing to this high octane fuel generated from this catalytic cracking process. So now they are replaced with the zeolites that way. And even many of those classical reactions were replaced by those conventional catalysts of the acid and bases by the zeolites. And one Few examples here I given. The linear alkyl benzene, the UOP, that company uses zeolites. Cyclohexanol, Asahi company uses HZ5 zeolites. Cumin synthesis, the Mobile company uses the zeolites. And ethylene imine, Nippon Sugobai, they use silica, barium, this kind of mixtures. So almost 180 different catalysts employed, 74 of these are zeolites. Out of the ZSM5, that is zeolites are largest group. Hundreds of industrial processes uses this solid acid based catalyst. The cumin process, for example, if you look at it, benzene and olefin gives at cumin. It is important since 1950s for phenol production. So initially they used aluminum chloride or sulfuric acid. Copious amount of acid waste was produced. The Hulls company, they developed a HF process. It was greener but dangerous. Then UOP came with the gas phase process using phosphoric acid and silica with the BF3 catalyst. The good but still corrosive. And then recently the mobile zeolite process where no acidic waste, no corrosive product, and almost 100% yield. And you can see almost every car has a catalytic converter where the platinum or palladium or rhodium catalysts were used to convert that unburned hydrocarbon, which gives that carbon monoxide, even the hydrocarbons, remaining hydrocarbons, they can be completely burned into CO2, or even NOx can be converted into N2. So you can see the value of this catalytic process in reducing the pollution in every car nowadays. And we have carried out one process where the conversion of inorganic carbonate to methane, in particularly the conversion of CO2 to value-added product. The idea here is that where the CO2, which can be fixed to carbonates, this again converted into CH4 or any other hydrocarbons, this on burning gives CO2, this cyclic process. Of course, there is a huge challenge involved in this. How to convert carbonate to methane, this process is a very unfavorable without a catalyst. And if you look at the energetic things, it's almost like a minus 200 kilojoules or kilocalories per mole involved with reverse reaction, carbonate to methane. And then, but CO2 is one of the a product which needs to be removed, or emission in all the exhaust emission, which needs to be fixed. If you look at it, oil and coal reserves for next 200 years, the CO2 emission would be a problem, because there are other alternative resources for the energy, though hydro, solar, wind, biomass, but they can only supplement and not replace at this stage. Hydrogen economy and methanol economy is still under progress. So every 12 days, the world consumes about 1 billion barrels of oil. This is in 2009, this report in Nanoliter group mentioned, which represents the release of almost 1 trillion pounds of carbon dioxide into the atmosphere. So one way of dealing with this problem is by recycling the CO2 into a high energy content fuel. But nature plays a very brilliant way. They use a CO2 so successfully as a synthetic building block in photosynthesis process. So you can see the CO2 and water, it produces the organic compounds. So this on burning with oxygen. The opposite side, CO2 and water. So the CO2 in the atmosphere is almost 2,500 billion tons. Huge amount. Photosynthesis removes 360 billion tons per year. Almost same amount is released by respiration or by death and putrefaction of plants or animals. Other important source burning of limestone to make lime for cement. For example, the calcium carbonate, it gives a calcium oxide and CO2. That is from cement industry, almost 200 million tons of CO2 released every year. And then possible solutions, sequestration, that's a CO2 converted to carbonate using calcium oxide and other minerals. Or you converted CO2 into urea and other hydrocarbons. So our idea was to sequestration, the CO2 can be captured to get carbonates, and then to methane, this again goes back to CO2. The important step here, the carbonate to methane, that is one of the challenging process. You can see that energy involved here. Then CO2 to carbonate, it's an exothermic, but carbonate to the methane route, it will be an opposite side. So we have used some catalyst, some carbonate, and to convert into CO2 to methane. So instead of going CO2, then fix it to carbonate and then convert into methane, we directly used some metal carbonates and then looked at how easily we can convert that into the product, methane, other hydrocarbon. So this is the experimental setup we have used. This is the reactor where we kept a catalyst. And this has to be carried out in terms of hydrogen, the reduction of carbonate to methane. So these products are collected and analyzed by gas chromatography. So there are various carbonates. We prepared mixed carbonates. So cobalt calcium carbonate, nickel calcium, iron calcium, these combinations. Of all the things, we found that cobalt calcium carbonate was the very effective one in converting calcium carbonate to CO2 and methane. So the idea here is that if you take this carbonate in presence of hydrogen, it gets converted into calcium carbonate and this oxide catalyst. So this one acts as a good catalyst to convert any carbonate into methane. So this methane, which can be again converted into CO2 by whatever that chemical process. And then this CO2 can be fixed into calcium carbonate. Then again goes back to the reverse process. But you see that you need a hydrogen for the reduction. So this hydrogen can be coupled with some ethyl benzene to styrene reaction, one way to make this industrially viable process. Or further, the CH4 alone will not be very valuable product. We have to think of converting CH4 into some other oxygenator product. So there's a huge challenge involved. One has to look into that if at all this process to be profitable. And the other one important reaction, oxidation by molecular oxygen instead of other oxidizing agents. Since the chief oxidant is a molecular oxygen, still effective catalytic system for the epoxidation of olefins, hydroxylation of aromatics, and selective conversion of lower alkanes are not realized using this molecular oxygen. Because when you use that oxygen as an oxidant, they are thermodynamically downhill reaction, exothermic, and leads to CO2 and water. So nature does wonder. The enzyme monooxygenase and dioxygenase catalyze this reaction very quite selectively under mild conditions. For example, there is a very nicely fixing this oxygen, the monooxygenate enzymes, which just single oxygen attached with the substrate. Dioxygenase, you can see this way, very effectively this reaction is happening in enzyme catalyzed reactions. But an industrial reaction where if you do with a molecular oxygen in presence of catalyst, you get a complete oxidation, CO2 and water. But we need a controlled oxidation to get hydrocarbons, but that is very challenging. So the partial oxidation to give functionalized hydrocarbons, the people are trying out in a different ways. How to control the full combustion, that is the key challenge in the industry. And also how to increase the selectivity of the particular oxygen, just like that nature does using those enzymes. The role of the catalyst, normally the activation of both hydrocarbons and molecular oxygen. Activation of molecular oxygen is predominant than the activation of hydrocarbon. So if we have to look for a catalyst, we should see the activation of molecular oxygen is important than the activation of hydrocarbon. So normally when you use the catalyst, the nature of the active oxygen species comes the electrophile and nucleophile, O minus, O2 minus, O2 minus, O2 minus. These are the nucleophiles, the atomic oxygens and electrophile. This oxygen is very important to get the epoxidation reactions. It adds to C double bond C bond, olefinic bond, the electrophilic addition to form a triplet biradical intermediate, which then converts into epoxide. So if the catalyst activates, we have to get this atomic oxygen at the ground state to get an effective epoxidation reaction if we want to do olefin epoxidation. This atomic oxygen can also abstract hydrogen, but abstraction of hydrogen is slow compared to the addition to the unsaturated bond. So monooxygenase, this enzyme produces this active oxygen species with the help of protons and electrons from the strong reducing agent. So this is the energy involved here, O2 activation. You can see that from molecular oxygen to get atomic oxygen, this delta H will be almost plus 119 kilocalories per mole. If you use a reducing agent, it drastically reduces, it goes to negative range. The hydrogen, it reduces to 1.4 kilocalories. And carbon monoxide, it comes to minus 8 kilocalories. And if acetaldehyde, if you use it as a reducing agent, it goes to minus 10 kilocalories. So the dissociation of dioxin requires a huge energy. It is like a 120 kilocalories per mole, but it is decreased remarkably by using the reducing agents. And the oxidizing ability of dioxin is enhanced kinetically in the presence of them. If you create O minus, it will not show electrophilic activity towards hydrocarbon. It will immediately abstract hydrogen. So this leads to unwanted product. You will never get that epoxide in the olefin epoxidation. Or even you won't get a hydroxylation reactions like benzene to phenol reactions. So the dissociative adsorption of dioxin on the solid catalyst accompanies with the electron transfer from catalyst to dioxin in order to compensate large dissociation energy. So you will see that the main active species on transition metal or metal oxide is nucleophile, oxygen nucleophile, O minus or O2 minus or O2 minus. So it is with this type of nucleophile, it is impossible to expect you can convert olefin to epoxide or phenol. So the olefin oxidation and aromatic hydroxylation needs a special oxidant such as hydrogen peroxide, O3, and other peroxides and peroxide to generate neutral electrophilic oxygen atom without additional energy. So in that case, you have to have a reducing agent to make such oxygen atom exothermically by leaving a water molecule, just like the enzyme does the reaction. So people trying out various ways. This is an heterogeneous reactions where the molecular oxygen is passed from outside of the reactor. The hydrocarbon is passed through the cylindrical reactor inside. So this oxygen permeates through and reacts with the hydrocarbon and gives the product. So various approaches people are using to get a functionalized hydrocarbons. But it is the combustion dominates in all these reactions, so that reduces the selectivity. Particularly the phenol production, where the benzene reacts with the molecular oxygen and gives that type of phenol. That was a very attractive reaction. And we have used one membrane reactor where we utilized palladium membrane. This is a palladium membrane, what you can see. This is a one shell inside where we pass oxygen and benzene inside that reactor. The outside of the reactor, we pass the hydrogen. So this is the palladium membrane. So the hydrogen known to permeate through hydrogen, the palladium membrane, and it can react with the oxygen coming through this way. So you will get at oxygenated species, even a hydrogen peroxide. This again reacts with the benzene to give that phenol. So we use this membrane reactor. This is the membrane which you can see the palladium is coated on this aluminum membrane. So this is the one what you are showing here inside the reactor. The hydrogen has to go through the, because hydrogen and oxygen you can't mix directly because there are explosive reactions often. So it is a safe way to pass the hydrogen from outside, and it has to permeate through the palladium membrane. And inside you will be passing this oxygen and hydrocarbon here, the phenol, the benzene, sorry. So that reacts with oxygenated species or hydrogen peroxide and OH species that leads to the phenol. So this was a very interesting reaction, the one-step conversion of benzene to phenol. Though industrial production of phenol comes still from cumene process. So this is one conceptual reaction to say that we can produce benzene, the phenol from benzene in one-step route. And the other important process which requires a still green process is a synthesis of hydrogen peroxide. So hydrogen peroxide is a very important chemical. Almost like 3 to 4 million tons are produced, which is used in pulp and paper bleaching, detergents, wastewater treatment, chemical synthesis, and so on and so forth. In China alone, now it's 1 million tons produced hydrogen peroxide. The famous route, anthraquinone auto-oxidation process, and the complex and toxic solvent system involved, non-selective hydrogenation, deactivation of hydrogenation catalyst, and the costly process. It is economical only at large scale. And again, then your transportation, you have to worry about it. Though it is it avoids explosive H2O2 gas mixture because you will be step by step you are adding. But it is economically still not very effective process. So this almost 95% of the global production of hydrogen peroxide comes from this route. So the other alternate, people try to do the direct synthesis of hydrogen peroxide from hydrogen and oxygen. This looks very attractive, very simple to look at it, but it is not that easy. So the process involves 3-phase reactions, and you have reagent gas phase reactions, reaction medium where water, alcohol, liquid phase is there, and then catalyst again solid phase. So there are multiple processes involved. And the big challenge here, you can see the hydrogen and oxygen giving hydrogen peroxide with the delta H for this reaction is a minus 136 kilojoule per mole. It's highly exothermic reactions. But the hydrogen and oxygen giving water even more favorable reaction, minus 242 kilojoule per mole, this reaction. Not only that, the hydrogen peroxide undergo hydrogenation gives water. That's also more favorable reaction than the direct combination of hydrogen and oxygen. And not only that, the hydrogen peroxide undergo decomposition to give water. So these all the side reactions will be a big problem to produce hydrogen peroxide directly from the hydrogen and oxygen. Any catalyst which favors this reaction of hydrogen peroxide also favors the other two reactions. So it's a big challenge. In fact, it's a demanding research for over 100 years. First patent filed by this Weber in 1914 for a palladium catalyst in water. Many companies are involved still, DuPont, Mitsubishi Gas Chemicals, Dow, Solvay, BASF, Universal Oil Products. So many companies are involved in this process. In fact, 1990, DuPont planned to commercialize investment, but it's not yet materialized. DeCusa and Headwaters, they announced the construction of direct synthesis plant in 2005, that again not commercialized. Solvay company, they are saying that, but still it involves a pressure. It's not like a more viable process. explosive mixtures, so direct hydrogen oxygen mixing. So the best catalyst so far, people found out the palladium and platinum, and also some bimetallic catalysts, AUPT and PDPT. They supported these catalysts on titania and silica matrix, or even carbon zeolites. So and carry out this reaction to get a hydrogen peroxide. But they're all noble metals. They are not cost effective. So replacing them with tungsten metal or partially with the tungsten metal will be a better way to reduce the cost. Even price of palladium almost like a $50,000 to $60,000 per kilogram, and it is still going up. So that's why the people try out with the various materials, substitute or add with the palladium with some other tungsten metal to improve its catalytic process. So we have tried with the palladium with the nickel with the different synthesis process, nickel palladium catalyst. And we are able to see that when a small amount of nickel is there in palladium, a kind of alloy bimetallic catalyst, it shows that a very high activity for the hydrogen peroxide production, almost a 300% activity compared to the palladium catalyst in the production of hydrogen peroxide, direct hydrogen peroxide from hydrogen and oxygen. So the challenge again here, we have to transport this catalyst and a support. We should not leach out. And for long-term stability, we have to work on that. So which is still a thing which we are working on it. So in fact, at the time, even people have reported palladium tin catalyst also used for direct synthesis of hydrogen peroxide with a high selectivity. But we are also able to see almost 95% selectivity for this reaction. But still water formation and these things, you have to reduce it. So finally, I would like to highlight again that principles of green chemistry, how the catalysis and the catalysts are very much useful in realizing these principles of green chemistry, in starting from waste prevention, atom efficiency, safe products, all those things. A good catalysis process can completely change this energy, the environment, giving us a valuable product with less pollution. So with this, I would like to close my talk. If any questions, I will be happy to take. Hello?
Okay.
Yes.
Thank you, Ishramurthy.
Yes, thank you.
So I invite any questions from the audience?
Sorry for the initial trouble.
Raji, are there any questions in the chat box?
No, sir. No questions in the chat box.
Oh. Anyway, they can even write to me if any questions if they have.
No questions?
No?
Okay. There are no questions. I think we can go to the next talk.
Thank you. If any questions, I'll be happy to answer. They can send by mail also.
Yeah. Okay, thank you, Ishramurthy.
Thank you for giving me a nice opportunity to present, share some of our work and others' work.
Thank you.
I need to come on.
Can you unshare? Yeah.
Where is it?
So the next speaker is Professor Jayanta Haldar, again from the JNCASR Bangalore. He had his education from Indian Institute of Science, Bangalore, and then he did postdoctoral work at MIT, USA. He works in the field of Where is it is given? Okay, he has several recognitions. I think the organizers have not given me the field of research and his research contributions. So what is given here is his recognitions. He has several recognitions to his credit, including the Sheikh Shakir Career Award, Fellowship, CDRI Awards, Ramanujan Fellowship, etc. So may I now request Professor Jayanta Haldar to talk about mitigating surface-assisted spread of infections in the times of pandemic. Jayanta, are you ready?
Yes, I am. Can you hear me? Hello?
Yeah, we can hear you.
Okay. Can you see my slide?
Yes.
Okay. Good evening, everyone. Thank you very much, Professor Ajay, for the introduction.
Your voice is not very clear. At least for me. Can you increase the volume of your microphone?
That is the maximum that I put in. Can
Okay,
you hear me now?
Yeah.
Yes. So thank you for your introduction. I always love to come to Kerala and deliver the talk at FCBS, but it is unfortunate that this year, due to ongoing COVID pandemic, we cannot come to your place and we need to have this program online. Before I start my talk, I would like to thank Professor Rao, Professor Balasubramaniam, Professor Das, and my friends Shubi and Joshi, and other organizers for this, inviting me to deliver this talk. It's a great honor for me to deliver this talk in this evening. This lecture will be a journey where I'll take you through human knowledge of infectious diseases and the different ways of transmission of these diseases. I'll also talk to you how the surfaces play a major role to spread and of different kind of infectious diseases, and how we can tackle or prevent this kind of spreading, which is especially so important during this ongoing the pandemic that we are going through. I'll also try to touch upon the challenges that we have been facing throughout, and especially at this moment. I'm sure all of you know this person. He is Hippocrates, was an ancient Greek physician. And in ancient time, people used to believe that diseases are caused by due to supernatural forces. And Hippocrates, as early as 400 BC, dismissed the supernatural explanation of diseases. And the knowledge of the disease and their cause, what we today had, its roots in the teaching of Hippocrates. And he said that the illness are contributed or attributed to the climate, soil, water, mode of life, and also the nutrition surrounding the patients. He's referred to as the father of Western medicine. And we start today's lecture with a salute to Hippocrates. So what do we know about the infectious diseases? We know that infectious diseases are caused by microorganisms like bacteria, viruses, like currently the spreading SARS-CoV-2 viruses, fungi. It can spread to fungi or protozoa or parasite. And this type of microorganism can enter our body and multiply within our body and causes the diseases, right? But how small of this microorganism can you see by our naked eyes? No, they are very small, cannot be seen by our naked eyes. Like if you take it like a bacteria, which is like a micron in size, or if you go to the viruses like SARS-CoV virus right now, as I said, that's spreading, which is around like a 60 to 140 nanometer in size. They're very small. We cannot see by our naked eyes. We need to see them by various microscopes, and various microscopes have been developed, such as normal light microscope, or scanning electron microscope, or transmission electron microscope, or fluorescence microscope, scanning tunneling microscope, atomic force microscope, or high resolution fluorescent microscope that has been developed. And various Nobel Prize has been given for this development of this microscope since 1925. And most recent one is that in 2014, the development of high resolution of fluorescent microscope. Therefore, this all sophisticated instrument with microscope, we can see the viruses and or bacteria, and we can study them, and we can understand various things so that we can be able to tackle or cure these diseases. But interestingly, this is how one of the earliest microscope looks like. And I'll take you through the discovery of these particular things. But if you look at the earliest evidence of infectious diseases was found in around 1100 BC. However, the microorganism was discovered more than 2,500 years later. And still, interestingly, the fact that microorganisms are causing the diseases, to understand that took another 150 years later. And if you look at parallelly, these milestone events that happen, another battle was always won. The battle was to how to discover the ways of tackling these infectious diseases. The first concept of vaccination that was introduced in 1796 by Edward Jenner. And then the concept of chemotherapy was introduced in 1909 by Paul Ehrlich. And the final breakthrough came in 1928 by the discovery of penicillin, the first natural isolated antibiotics by Alexander Fleming. But however, all through this history and even today, the pathogens have continued to challenge the human intelligence. There has been emergence of new pathogens like a SARS-CoV. This kind of new pathogens are coming. Sometimes the emergence of old pathogens coming at different form, and then drug-resistant pathogens. For example, in last century, so many classes of antibiotics were discovered. But after overusing or misusing these antibiotics, bacteria develop resistance to all classes of antibiotics. A new drug-resistant bacteria is always threatening to mankind. So therefore, the battle against pathogen is always won. Now I'll take you through this earliest evidence of infectious diseases that happened, and then how the microorganism discovery that led to our understanding of the infectious diseases. If you look at this, the earliest evidence of infectious diseases that has been found in a mummy of Egyptian king Ramses V. In his face, you could see the smallpox marks are visible. And all through history of smallpox has been a deadly disease. We know it caused more than 300 to 500 millions of deaths in the even 20th century alone. But fortunately, through a lot of research, worldwide smallpox has been now eradicated completely. And the last natural causes of smallpox that happened or reported in 1977. So that is very good news. If you even look at these particular things, you might have heard this rhyme, ringa, ringa, roses, pocket full of posies, hush, hush, we all fall down. I'm sure all of you, all of us have heard these rhymes. So this rhyme has been associated with the diseases which happened in England in 1665. And these diseases was so deadly that it was called as a Black Death in England. And this causes by this bacteria, it's called Yersinia pestis. So these ringa roses imply the rosy rash that was a symptom of this disease. And the pocket full of roses is the one type of flowers you carry to protect from these diseases. And we all fall down exactly that what happened actually. Many people who are sick died because of this disease. This plague was first plague was first recorded as early as 160 CE and has caused more than 75 million deaths worldwide. And today, the plague occurs less than 5,000 people in worldwide, which is quite good compared to the thing that happened in 1665. Now, today we know all the infectious diseases are caused by microorganisms, and we have, as I said, that we have a sophisticated instrument to view them and define microscope, define system, right? The microscope was first discovered, as I said, this by a gentleman who was first discovered, and this is his own microscope he designed, and through this microscope he have seen this microorganism, and so you give a name, is called animalcules. It looks like a very little tiny animals roaming around. So that was the name. And at the same time, around that time only, there is another person, Robert Hooke. He also designed his own microscope. Through this microscope, he have also have seen this microbe, and then he coined the term cell. So therefore, this microorganism that discovered happened around that time, 1700. But it was very later, as I said, another 150 years later, people discovered through the various research that actually microorganism can cause that disease. So now we know that how and when microorganisms are discovered. Now we'll see how microorganisms are associated with these diseases. As I said, that for a long time after discovery of microorganism, people used to believe something as small of like microorganism can cause the disease to this big human. How it is possible? One of these interesting explanation of disease at that moment is called miasma theory. People believe that disease are caused by bad air, not any microorganism. But it was only in 1800, 19th century, that germ theory was introduced, discovered, or established. People believe that diseases are caused by, as I said, bad air. But this 19th century various scientists, through their research, they said they know the bad air cannot cause the diseases. That there is a microorganism which can cause these diseases, and not only in human, animals, and other living hosts. So I'll take you through some of this pioneer research of this set of people who contributed to this established the germ theory. The first one is an Italian entomologist who worked on the insect, like Agostino Bassi, the first person to state the germ theory, about the germ theory. He stated that microorganisms can be cause of disease. He discovered the causes of the death of silkworm with a very small microorganism, fungi. And in 1844, around that time, he also stated that idea that not only animals or insects, but also human diseases are caused by other living microorganisms. For example, measles, syphilis, and plague. The next comes through a Hungarian physician, Ignaz Semmelweis. In 1847, he initiated hand washing and washing of medical instruments. He showed that this reduced the mortality of pregnant women during delivery from 18 to 1%. Semmelweis' observation conflicted with this established scientific community or medical opinion of that time. Nobody actually agreed that one. His colleagues, other doctors, thought that what is this nonsense this gentleman is talking about? Why do we need to wash our hand or our medical instrument? And but nobody actually given any importance. But after his death only, people have accepted his finding and this observation, and he's been called as a father of infection control. And today, I'm sure we have learned from his understanding, and that's why probably during this pandemic, we are continuously washing our hands. It's been recommended we wash our hand frequently so that we don't get the infection or we don't spread the infection from one person to another person. Then goes to the 1854, this English physician England, John Snow, had traced cholera outbreak in London and through the water sources. And he said that he established this link between this infection and water as its medium to spread. By this finding, he established the fact that the water can be carrier for the pathogens which is causing the diseases. Water itself cannot cause the disease. But at that moment, people used to believe that actually means the water or bad air was causing the disease. But he's the first person who proved that no, that is not the case. The microorganism only was causing the diseases. Then goes to the great French chemist and microbiologist, the Louis Pasteur. His contribution in science is enormous. Around 1860, he discovered the principle of vaccination, microbial fermentation, pasteurization. He performed experiments that show that without contamination, microorganisms cannot grow or develop. He demonstrated that he sterilized or sealed flask, nothing ever happened. But this sterile flask, if it is open, if the microorganism goes inside, it starts growing and contaminating the things. Pasteur also discovered that heating milk to a high temperature and then quickly cooling down before bottling it can stay for longer time. And that is still we are doing as a household every moment, every day. And different food industry to drinks, people are using this particular technique, pasteurization. He also connected microorganisms causing the diseases. He created the first vaccine, even for the rabies and anthrax, and he has been called as a father of microbiology. And then goes to 1870, British surgeon. He promoted the idea of sterile surgery. Lister successfully introduced the carbolic acid, which is now called as a phenol, which can be used to clean different surgical instrument and also the clean the wound. And for that, he could cure the disease, to prevent the disease, infection diseases. And that's why he's called as a father of modern surgery. Sorry. And then goes to the person, the great French chemist again, and the Robert Koch. And he in 1890 he established the link of specific microorganisms with the specific disease, and rejecting the idea of spontaneous generation of the disease. That there is no spontaneous generation of any kind of disease like that. That microorganism actually that causes the diseases. And he also worked on anthrax, cholera, or TB. And he initially people used to believe that tuberculosis, the TB, was an inherited disease. But he is the first person who convinced that no, diseases are caused by this microbacteria. And he has tested using the guinea pig model and then established the whole thing. And he has been given as a Nobel Prize in 1905 because of his this discovery. So now we know that how these infectious diseases are spread. We know that if you have not having the if you're having the contaminated food or water, you're not having clean water, you can get the infection. Suppose diarrhea, bacterial infection in the intestine, for example. This type of transmission of infectious diseases can happen even through the blood or body fluid, for example, HIV. Or it can happen through airborne when you are cough or sneeze. If you have a respiratory infection like the influenza virus or like COVID, SARS-CoV, this type of droplets or this type of aerosol comes out from your body, from your nose, mouth. And if you are, but the person next to, very close to you, can get directly from through these droplets, or these droplets can accumulate it onto the surfaces and then you can get this infection as well from by touching this. Then there is a defined diseases which can be spread through a vector-borne, like a mosquito for malaria, suppose dengue. And there are also the direct contacts, it can be spread. As I said, that many cases, many times, the bacteria or virus get deposited onto the surfaces, and we get infection once you come in contact with these contaminated surfaces. And it has been found that more than 75% of infectious diseases actually spread through these contaminated surfaces. And this is very common in hospital, where this type of pathogens or bacteria viruses can deposit it onto this patient bed, or various like tables, or these surgical tables, ventilator, different type of equipments that is there present in the hospital. Or it can be this type of pathogen get deposited onto this type of catheter or needles, or different type of implants the doctor put it into the patient body. So this is quite common. This surface-related infection is quite common. And this is very common in a hospital area, in the sense, as I said, this type of pathogens are all over the places. And what happened, the many cases, like when you go to the hospital, you probably have a different kind of disease, nothing to do with infectious disease. But once you reach to the hospital, you get this infection from the hospital, because this type of pathogen or this are associated, are near the hospital and different places, right? And that is called the hospital-acquired infection or nosocomial infection. That means infection that have been caught in hospital, but the secondary to the original condition of the patient, you might have some other diseases, nothing to do with the infection diseases. You have gone to the hospital to get cured, but so unfortunately happened that once you reach there, you get the infection from the hospital. This is quite, as I said, even in the United States, if you say that 1.7 million infection happen and more than 99,000 people die every year, where the best medical facility probably there in the world, in US, and still that is happening. So you can imagine how difficult, what is the situation in even developing country like India even, or any other developing country. We have found that 100 hospitalized patients, the 7 developed countries or more than 10 people in the developing countries and get infection because of hospital-acquired infection, where you did not have any contribution in the beginning, you did not have any disease of infectious disease, but you reached to the hospital and got the infection. That is important. So the most of these hospital-acquired infection are related with the surfaces, because those, as I said, those bacteria or viruses get deposited onto this type of, not only this type of surfaces, but different type of urinary catheter or central venous catheter or orthopedic implants that doctor put it to the patient's body. And if you can see, the more than 30 million urinary catheter being used, or more than 5 million central nervous catheter being used every year, and they're highly prone to this type of infection. And there are many other catheter, many other type of implants, all the patients require for different purposes, and these are highly prone to this type of infection, and therefore you get this infection. So one of these most important problem or more challenging problem of this biomaterial associated infection is the biofilm. What happened, even single bacteria if attached during this operation, attached onto these biomedical devices or this catheter, and then if it goes inside the patient's body, it starts onto the surfaces, start dividing onto this one and then proliferating, and they creating some type of matrix, some type of polymer, some type of matrix, and then hiding themselves from this. So when you take this any antibiotic, actually this antibiotic cannot penetrate to this type of masses and cannot kill the bacteria which is hiding within this one and covering this entire biomedical devices, and then failure happen. And also even in the bacteria, the antibiotic can cross this matrix and go inside and kill the bacteria. There are another kind of bacteria which is made up, we call them metabolically inactive bacteria, means they are sleeping. So they cannot be killed with this known antibiotic. So therefore they go and start spreading to the other part of the body of the implant and create it. And this is one of the examples I have given here, where this pacemaker was put it into the patient's body, and the patient was fine, has been released from the hospital, and after a few years, patient was living very nicely, and after a few years, the person had some elbow injury. From there, the bacteria has gone inside in his body, and now it has gone to the circulation, and then bacteria start accumulating onto this pacemaker and forming this biofilm. You can see huge amount of bacteria, the staphylococcus areas, the bacteria, and accumulating onto the pacemaker. And after that, even through the high dose of antibiotics, could not save the patient, and the person died. So this is very unfortunate. This is one of the major challenge in the biomaterial associated infection, one of the biofilm that I've been talking about. Now I'll talk about little about the virus that we are going through, the pandemics. The two most notorious respiratory infection viruses, which is called influenza virus, that we know that happens every year, and then another is what is happening, the SARS-CoV-2. Both are respiratory virus causing the respiratory disease, and flu is caused by the influenza virus, we know, and COVID-19 caused by the SARS-CoV-2 viruses. And these two viruses, their symptoms, initial symptoms are quite similar. They have fever, cough, myalgia, and then very difficult to distinguish whether you have a flu or SARS-CoV. Therefore, we need to have a testing done. And it can be done through antigen test or artificial test to confirm what kind of diseases happen. And it's been found that COVID-19 is quite more dangerous than we understand right now. There are more serious life-threatening respiratory pathogens and causing lung injury. This COVID-19 is although more than 40 to 50% are asymptomatic patients. They are the people who are actually spreading these diseases unknowingly. And then there are a certain percentage of people are getting very sick and having serious illness and even pneumonia, and people are dying. And that's why it's happening at this moment, this pandemic. And if you see these viruses, two viruses, they are both enveloped virus. They have a lipid membrane, both surroundings, and around 80 to 100 nanometer size. Influenza virus similarly like 60, 140 nanometer is size. In case of influenza virus, you have a 7 to 8 negative standard RNA genomes that it has, whereas in SARS-CoV you have a single RNA, positive standard RNA segment. Both the viruses can be spread as a droplets when you cough or sneeze when you talk, and it can be directly to the person who is close by, or it can be contaminated with the objects, different type of surfaces. This type of droplets can be positive, and then you go and touch this one, and once you touch, and with that hand you touch your nose, eyes, and mouth, you can get the contaminant, and you can get the diseases, both this kind of diseases. And if you look at in case of influenza viruses, there are multiple pandemics happen. Even 1918, the Spanish flu, which is the H1N1, which caused 50 to 100 million people died. More than the people died in World War I and II together. Even 1957, Asian flu happened. 1968, that Hong Kong flu, which is H3N2, different type of viruses. And there are few, this thing happened. Even the few years back, 2003, the H5N1 avian flu. The flu has come from the bird to human, or swine flu, even H1N1 in 2009. That happened is a mixture of this virus, a mixture of the avian flu, pig flu, and also the human flu. And it come and that became very, but could not, unfortunately could not spread much like this type of viruses. But we have the regular seasonal flu, which is causing more than 5 to 10% of the total world populations, which is like 3 to 5 million people are getting this severely ill, and people who 250, 100,000 to 500,000 people are dying, even with these viruses, influenza viruses. Similarly, even in case of SARS-CoV, we have previously coronavirus, some of coronavirus happened, but they did not spread much, did not cause much diseases, but the things, whatever is happening, that's COVID-19, SARS-CoV-2, which is already infected more than 60 million people worldwide and killed more than 1.5 million lives. And it has all over the globe actually spread. So these all viruses, we could see that they spread through the droplets or even quantum surfaces onto a deposit onto surfaces, and from the surfaces it can spread from one person to another person. We could see this type of viruses can live at different surfaces at a long time. You can say that the SARS-CoV virus is even on the tissue paper, it can live even 3 hours. Stainless steel, it can live even 7 days. Plastic or banknote also more 4 days. Or this type of personal protective PPE materials, it can survive even more than 7 days. Similarly, in the this influenza virus can live for defined days on this different kind of surfaces. So therefore, this once it get onto this surface and you touch this surface, you can get the infection when you are touching your nose or mouth, and as I said, and get the diseases. So therefore, it is important that we take care how we take care of these surfaces. If it is can be clean always, the surfaces we can take care of the infection. So there are 2 ways that can be done at this moment. One is if there is a contaminated of surfaces, so you can have different type of materials which can clean this surface. Like right now we are washing using soap to clean our hand. Similar type of soaps can be used to clean the surfaces as well. We use the sanitization of alcohol to clean sanitize our hand. Similarly, the alcohol can be also used for the cleaning the surfaces. We can have the different type of little oxidizing agent like bleaching agents or hydrogen peroxide. This type of hydrogen highly oxidized agent can be used to clean the surfaces. Or you can be treated with the surface, can be treated with the UV that can take care of the this type of, that can kill this type of bacteria or viruses onto the surfaces so that it is called all a sterile surface. There is another way that we can do. Is it possible to make the surfaces inherently antimicrobial so that as soon as it gets deposited, this bacteria or viruses, it should be able to kill its own, right? That is also possible, and I'll take you through that. The people have tried to do different way. One is like people have used this type of molecules like silver ions, iodide, or antibiotic, this type of molecules impregnated within these surfaces. And what happened, this type of molecules can come out and kill the bacteria or pathogen viruses onto the nearby, onto the surfaces. So it's called release valve mechanism. It can release from the surface and kill. And there is different product like a pacemaker surfaces. This type of antibiotic has been put it with the polymer and can be coated. There are silver, titanium, dental, orthopedic materials can be used for coating this type of surfaces. Then titanium alloy with the gentamicin antibiotic can be coated. Or for this type of antibiotic, I also coated with this type of polymer, hyaluronic acid polylactic polymer for orthopedic implants, and those are in the market. But there is a certain limitation with this particular technique. As I said, it's a long-term application because this type of molecules get released from the surface and kill it, and over the time it get exhausted, right? It's a non-long-term solution. And specificity of loaded antibiotic limit the broad spectrum activity. That means different antibiotic, this can be killed with the different antibiotics can be used for different to killing different bacteria. So you don't know which actually bacteria is getting deposited onto this type of surfaces. So it's very difficult. You need to have the antibiotic which can kill different kind of bacteria. That this has to have the broad spectrum activity, otherwise it's not going to work. And that loaded drug may be ineffective against drug-resistant bacteria. As I said, the bacteria already developed resistance to the known antibiotic. And if this antibiotic is loaded with this one, and bacteria already developed resistance to that, it's not going to work. So there is different kind of challenges. And also over the time, as I said, this release and killing, over the time is the concentration of this molecule onto the surface is getting reduced. And that actually induces further development of the bacterial resistance. And that is a huge problem. But this is the technique that is there in the market at this moment to take care of the infectious diseases. So this is one thing. Second thing people have thought, is it possible to have the anti-adhesive coating? People have made this type of polymer covalently attach onto different type of surfaces. And these surfaces, what happened, this type of pathogen when it comes, they repel. They won't allow to attach onto the surfaces, okay? And therefore, people have made this type of, and for example, you can see this polymer when attached, Without the glass surface, you can see so much of bacteria onto the surface and contaminated the surfaces. But when you coat it onto this one, you can see there is very less amount of bacteria can be attached onto the surface. But again, this can also have a certain limitation in the sense very difficult to modify the surfaces with this type of polymer, because different surfaces need different type of chemical reaction. It's not that easy. And efficacy is not absolute in the sense that it's not like the completely repelling all the bacteria. Still there will be some bacteria and can contaminate, and this one. And there is another associated problem that when you coat it with this type of molecules and impregnate in our body, the devices, but our cells also will be repelled, right? And that is not good. Your tissue should integrate onto these our devices, and but that doesn't happen. Therefore, this is also a limitation in this technique, but this is quite a good one. The third approach people have taken, the people have used this type of polymer, cationic polymer, conjugated onto the surfaces. And once this bacteria or virus get onto the surface, it can kill. So it's called the contact killing, because on contact only it can be killed, the bacteria or viruses. But again, the limitation can be the covalent modification we need to do the surface, as I explained, that has a, and there are different other type of limitation can be there. Once the dead bacteria accumulate onto the surface, that can induce the biofilm formation and many other things can happen. But these are the various techniques that been tried to adopt and try to use it for taking care of the infectious diseases. The next few minutes, what I'll tell you that what we do with respect to this infectious diseases and how to take care. We have been doing in our lab various ways to take care of these infectious diseases. One is that how to prevent these infectious diseases. And then another is that if you have the infection, can you have the better drug to treat this infection? So towards that, we have been working various like synthetic antibiotics we are trying to make. We are making the molecules which can in combination can be given with the old drug and can we make it again active and bring it to the market to treat the patient. We are also working on developing different type of small molecule as a drug which can take care of this infection. And today I'll talk to only about this antimicrobial coating onto the surfaces which can take care of this infection that I'm talking about, this surface associated infection. Is it possible? And I'll restrict myself to this one, to our contribution. Towards that, we have developed different type of polymer inorganic antimicrobial paint. For example, we have developed this on non-biodegradable paint, which will be soluble in organic solvent and can be painted onto the different type of surfaces. We can say this is the plain surfaces where there's so much of bacteria contamination happen. But when you paint the surface with our compound and spray the bacteria, we can see the bacteria cannot live, cannot survive. Similarly, you use the Asian paint and put the surface and you can see so much of bacteria. But if you put our compound some amount with the inside the Asian paint and paint our surface and spray the bacteria, you can see the bacteria cannot survive. So therefore, this type of system can be used to paint out various type of surface. We have used also biodegradable paint, where this type of polymer can be painted onto the surfaces. And we can see if you don't have our compound, there is a contamination onto the surface of various bacteria or this is fungi. And when if you have the potato, there hardly any bacteria can be seen. We have been working on different kind of other system where initially this can kill it, but over the time our coatings can degrade and they release those kill bacteria from the surfaces and can be active continuously. And we have been also working on the different polymer inorganic nanocomposite, which can be used further for taking care of this type of infection. But I'll give only one example. For example, this type of compound, when we have put it and sprayed the bacteria, you can see this plain surfaces, so much of bacterial contamination happen. But when you put our compound, put it with this surface, we can see the bacteria cannot survive. And we can see this is the biofilm I'm talking about. When the huge amount of biofilm formation happens, this much thickness of bacteria biofilm onto the surface happen with the plain surface. When you have put it on the surface, we don't see single one or two bacteria onto the surface, both bacteria as well as the fungal cases, we could see the similar effect. Then we have how we want to understand how this compound, which is coated onto the surface, can kill this type of pathogens. And we can see this, for example, This is the plain surface. You see the bacteria, their size and nice, their structure. But when we put it into the surface and bacteria, we put it, you can see they disrupt completely. They destroy their structure and kill everything is came out from their body and everything leaks out and kill the bacteria. And we have done various other techniques to prove this type of compound has the ability to kill by disrupting this bacterial membrane, the bacteria envelope and kill the pathogens. Now we have also coated this type of molecule onto the catheter. This is polyurethane catheter the doctor use all the time for various purposes for the patient body. And we can see when we put it with our compound and put it into the mice body, and we can see the huge amount of infection happen into the normal catheter without our compound, around 10 to the 8 huge contamination. But when you are coated with this one, you can drastically reduce the bacterial burden. More than 99% of this bacterial burden can be reduced. And when you analyze, after taking from the mice body, analyze this one catheter, we can see they can, in the plain catheter, huge amount of bacteria biofilm formation happen. But when we have a coated surfaces, we don't see any bacteria onto the surfaces at all. And therefore, this type of compound can be coated onto the surfaces and then kill the pathogens and take care of the infection. The last example that I want to give, which is very recent, we have developed the small molecules which can be dissolved in either in organic solvent or water system. And you have this type of surfaces, okay, different surfaces like cotton, mass, plastic, rubber, different polyurethane. You dip it into that, or you put the compound as a drop onto the surfaces, and then you irradiate. Once you irradiate, this type of compound get covalently attached onto the surfaces, and then you wash it out. And then we want to see whether these coated surfaces can kill the pathogens or not. When we did, now we've taken these coated surfaces, put the bacteria onto the surfaces, and incubate for some time. And then these coated surfaces we drag onto the agar plate and see whether bacteria is alive or not. So we have taken the compound, the coated surface as well as the control surfaces without putting our compound. And we can see this is coated surface and this is uncoated surfaces. Uncoated surface, normal plain surface, you can see huge amount of bacteria are accumulated. Whereas the coated surface, you don't see any bacteria. We have done different kind of drug resistant bacteria, this type of drug resistant methicillin or this of vancomycin resistant bacteria. None of them actually have this completely kill this our coated surfaces. Whether it's polyethylene surface or rubber surface, paper, leather, surgical mask, we could see all the cases. In uncoated one, huge amount of bacteria are present, whereas coated surfaces you don't have that bacteria cannot survive. It can kill. It can kill within few minutes, 30 minutes to 45 minutes it can kill. Then we want to see whether these coated surfaces can kill, like a polyethylene or surgical mask, can kill the different type of fungi infection. Immediately you can see, this is again, we have to put the drop of fungi onto this one, and then keep it for some time and then drag onto the other plate. We can see the uncoated plain surface, so much of these fungus are growing. While in the coated surface, we don't see any fungi present onto this coated surface. Similarly, the surgical mask, when you are coated with our compound, you can see that it is uncoated one, so much of fungi are present. By the coated one, you don't see any fungi present into this one. Therefore, this type of compound not only can kill bacteria, it can kill the fungi. Now we want to see this type of system can kill the viruses or not. We have chosen two notorious respiratory infection, the viruses, as I said, the influenza virus. And then when we two kind of viruses like which causes the, this is the virus which caused the Spanish flu in 1918 and this pandemic. And we also have another human virus, both the H1N1 and most pathogenic viruses. And we can see that this type of coated surfaces we have taken. And this is uncoated surface. You can see this all dot. We can see that those are live viruses when we infected the cells. But when we coat the viruses incubated with our surface and then try to infect onto the cells, we don't see the coated surface, any virus left. In case of this this virus and as well this virus, a different surface, polyurethane, surgical mask, polyethylene, you can see all the cases. Huge amount of viruses are present onto this type of mask or this type of surfaces. But when we are coated on with our compound, we don't see virus cannot survive. It can kill completely the influenza viruses. Now we want to see whether this type of surfaces can also kill the SARS-CoV, which we are right now going through, and that is most important. Yes, within collaboration with the Harvard Medical School and the Mass General Hospital in Boston, we have done the same thing. These two surfaces we coated and incubated with this SARS-CoV-2. And then this is the coated, this one panel, and this is uncoated. You can see the virus still live onto the uncoated surgical mask. But when we have coated with our compound, we don't see any living of the viruses onto this one. So therefore, if you have a mask for this type of surfaces, can be coated onto the our this type of molecules, and probably can take care different type of respiratory virus like influenza virus or COVID. Also can take care of bacteria and fungal infection. So this is like a really true antimicrobial surfaces which can take care of different kind of infectious diseases. With this, I like to say conclude my talk by saying that yes, the whole world is facing these pandemics, and this is important definitely. And we are in this situation right now, and we are having talk on there today. But with that, not only that, in a silent way, there is another kind of things is happening, which is so serious, and we don't realize probably, which is called antimicrobial resistance in general. It's been found that more than 700,000 people are dying annually because this antimicrobial resistance, the drug antibiotic used to be there, it's no longer active, doesn't work anymore. And people have anticipated that by 2050, it is 10 million people are going to die. And so unfortunate that India is contributing towards this highest. And if you see from this map, you can see that India has been identified one of the hot spots where different kind of infectious diseases are emerging all the time, whether it's from pathogens from wildlife, non-wildlife, or the drug-resistant pathogen or vector-borne pathogen. India is quite red spot, we can see. So this is so unfortunate, but this is the fact that we are in this situation. And I believe some of you, after finishing your bachelor or master, or even doing after your PhD, you during your postdoc, you will be able to, be part of this journey, and will try to solve this and tackle this infectious disease collectively. With that, I like to thank my group has contributed. As I said, only one part of the work that we have spoke about respect to infectious diseases. I'd like to thank other students, previous students who has contributed enormously to this work, and this my collaborator. I also like to thank Professor Rao, who has constant support to our research. I'd like to thank funding agency for various funding for supporting our research over the years, and especially where I now respect to the COVID related support from CSIR and then Indo-US project. With this, I would like to thank, saying that please wear mask, wash your hand occasionally when you can, and keep distance, be safe at home, and be healthy. With that, thank you very much for your time and attention.
Okay, thank you, Jayanta. It's a very timely and very useful lecture, especially at the time of pandemic. I can see a lot of questions, coming in.
Happy to answer.
So, shall I read that all the questions? There is a question from Betty. Rajesh, shall I read it?
Yes, sir. Please go ahead, sir. Please.
Why coronavirus affect people differently? Because some of them are asymptomatic and some of them have mild infection, but some of them have,
Exactly. As I said, that is very difficult to say at this moment. We don't have much information. But the fact is that more than 40 to 50% people are asymptomatic. And they are the people who actually unknowingly actually spreading these infectious diseases. Whereas other 15 to 20% people are becoming sick, they're having and then recovering over the time. But unfortunately, there is a certain percentage of people who cannot come back because causing serious illness and respiratory illness and multi-organ failure, and then even the viral pneumonia. followed by the bacterial pneumonia. The various serious things, and at this moment, actually, we don't have the answer. Why it is so defined. There are many diseases like influenza also came and causing every year, but we don't see that kind of situation, right? So therefore, I don't have any answer to this one because it's not known that why, but the fact it is there. Yes.
Okay. There is another question from Snigdha. What is the action of COVID-19 in our body? Which tissue or cell this virus focuses? What will be the factor help?
Yeah.
What
So
will be factor help the virus?
Yes. So initially, we know that this is a as I said, the respiratory disease, as I said. But thing is, once it goes into the body, through the nose, through the respiratory system, now it's been found out it not only can infect our lung or tissue, but there are many other organs it can infect, like even a brain, spinal cord, or other places, even kidney, liver, even intestine, it has been found. So therefore, this type of receptor that is present into which is required to virus to get into SC2 receptor with the viral spike protein that is present, and it is now found out at different tissue. It is no longer restricted to the respiratory disease, although it is going and mainly causing the respiratory infection, but it has been found and causing the disease in other tissue as well.
Okay. There is a question from Ammu Rosen-Jos that can any of the surface modification concepts for antibacterial activity useful for virus also?
Yes, as I said that the last example, I have given, one of our system, when we coated covalently with this different kind of even PPE materials, like a mask, head mask, and then other surfaces, we could see when we are tested, not only can kill the bacteria or fungi, but also can the respiratory disease like an influenza virus we have shown. Now we have shown with the COVID-19, actually the virus which is causing the diseases, the human COVID-19 viruses. And so therefore, that was the goal, and that is we have shown now with the collaboration with as I said, the Harvard Medical School and MIT, and we have shown with this. Yes, indeed it can.
Mm-hmm. There is a question from Archana Santosh. Could virus evolve to become less deadly or less dangerous? I think what she means is the mutation.
Yeah, absolutely. That is possible, but this is all possibility. At this moment, we are just nowhere close to say anything or answer to any of this question probably, but because there are many viruses over the time it get mutated and can be dangerous or can be non-dangerous as well. So we don't know at this moment this particular virus, which way it will go, but there is a possibility. It's known for other. Yes.
There is a very basic question from Gian A. Varghese. What are main differences between bacterial membrane and virus membrane?
Okay. So there is a huge difference in the sense, the bacterial envelope, bacterial membrane are mostly negatively charged membrane. They are this made of the lipids, which is like mostly like negatively charged lipid, like phosphatidylglycerol, phosphatidylethanoamine, cardiolipin, they are highly negative charged lipid. And even in case of gram-negative bacteria, the lipids is a special lipid. They have another membrane, which is a special lipid. LPS is called lipopolysaccharide, highly negatively charged lipid with a lot of sugars associated on this. And in case of the virus, the membrane, the lipid comes from our body, because from our cells when get infected and it's coming, parting is happening, this lipid is taken, the membrane composition taken from our lipids. So therefore, our lipid is mostly like most of the cases is a deuterionic lipid, like phosphatidylglycerol, phosphatidylcholine, phosphatidylethanoamine, and different type of other composition of lipid, but mostly deuterionic lipid. So therefore, there is a huge difference between this bacterial membrane lipids versus our membrane lipids. Yeah.
Okay. There is another question. The reaction between polyurethane coated surface and the virus.
Yes. At this moment, it's very difficult to say, but what we anticipate, because we have tested, we have done with respect to bacteria, we have done respect to fungi by saying that we have proved it, that this kind of molecule, this one, the coated molecule, coated surfaces with our molecule can interact with the membrane that I just spoke about and open up and kill the bacteria, and define way that we have proved it, this one.
Yeah, I saw that.
So therefore, that we anticipate probably this type of compound will be able to kill a similar way by interacting with the disrupting the viral envelope, viral lipids, and kill the viruses. And it is also known that the virus envelope, when you disrupt, there is no mechanism. Virus cannot repair it, but it's a bacteria ourselves. There is a mechanism still. If we have certain kind of damage you do, there is a way to repair it if you're not really damaging too much. But in case of virus, they don't have the repairing system. So therefore, and we believe that is happening, but we don't have at this moment any proof other than saying that yes, indeed it can kill.
Okay. Is there a possibility of formation of biofilm in the coated surface with a dead bacterial cell? The question from Sneha Raj.
Yes, if we have a fully cationic coated surfaces, I have mentioned in one of the slides, over the time these bacteria get attracted onto these surfaces and kill it, and then the dead bacteria can deposit it onto the surfaces, and over the time, on top of this dead bacteria, the other bacteria, live bacteria start coming and can start forming the biofilm. And that is one of the limitation or drawback of this cationic coated polymer coated surfaces. Now we have a system now. What happened initially, this polymerase system coated surfaces is cationic so that it can bring it and kill it. But over the time, in presence of different pH or in the enzymatic, this coating start getting degraded, okay, from the top, and then releasing this dead bacteria. So the all regenerating surfaces inside whatever and try to kill it, and it can go for longer. So indeed, yes, that is possible, and that is the one of the drawback. But we are working, and other people also working, try to various way try to address these issues. Yes.
Okay. Can you suggest the most reliable method for reporting the antiviral effects?
Can you repeat, please, once more?
Can you suggest the most reliable method for reporting the antiviral effects?
Yeah, so there are various ways antiviral effect is people do. Like even if you do the RNA sequencing, is how much RNA are there present, you can do it. But that doesn't give the information of whether the bacteria virus is live or dead, just quantification of RNA. The type of experiment type of method that we have done is called the plaque forming unit. That means you need to have living cells. You take the bacteria virus soup after treating, and then infect the soup, infect these cells, and see the number of plaques that develop. That means this plaque only can be developed from the live viruses, not the dead one. Therefore, we will be able to quantify what is the number of viruses, live viruses are there or not after treating with the compound. So this is the one of the best method probably can be measure the antiviral testing. Yes.
Okay, there is a question from Sunil. What to do if you get a rash or infection to hand sanitizer? I think Sunil may be asking.
Yes, that's the thing. People propose. Exactly, people propose that maybe you are continuously using hand sanitizer. It's not very advisable. It's not that good. When you don't have any source of water or soap, then therefore that time probably you can carry and use it. But if you have, if you are at home, if you are a place where you can easily accessible with the water and the soap, you should wash with the soap, and that will be fine. And I agree with him. If you keep on using, people will be having that. Some people are quite sensitive with their skin, and that can create problem. And try to reduce that. When you cannot have option, only that time you use it.
Okay. There are two more questions. The last but one is from Aditya Prakash. It's a rather long question. If you check recent years, every year we have to face several kinds of infections. Is it only because of changes in the environment, and in our life, or any other scientific reasons behind that? Is it possible to use the polymer-coated catheter against COVID-19?
Yes, thing is that there are multiple questions, looks like, or at least more than two I could see. But I'll try to answer this one. Yes, indeed, the last one, let me answer. Yes, indeed, this type of systems can be coated onto the catheter, and if catheter-related infection there, it can take care. But respect to the COVID, we are looking at mostly the outside, like a mask, gloves, or this type of PPE materials, or the hospital places, or the bed and other places which can be coated where this type of virus can deposit when some patients or some person is coughing or talking or sneezing and can kill it. Nothing, not much to the catheter probably, but it can be similarly it can be coated, because we have taken different type of surfaces and we have coated and we have shown that it can kill. So therefore, this is possible that you can take care of the catheter related things. The first question is that, okay, why that every moment we are facing different type of infection and a new infection? As I said, yes, not only the new kind of infections is coming, not only that the old infection different form they are coming, and also that the drug resistance, as pathogens I told you, that is evolving and that is coming. And especially if we look at a developing country, or like even including us in India, why it is so, and there are multiple reasons. The sanitization that we follow, because COVID actually teaching us a lot how to take care of ourselves, the population that we have, and then our healthcare system we need to improve, and other things to actually take care of this one. Because many, even if you look at it in village, people have not having proper water. Forget about that, they are having the distilled water that we take at home right now, or the Bisleri and other water. Many places in India, in a village, we don't have the proper water system. And forget the people will be having from the pond or whatever, wells and other places, and try to have. Imagine if you are not having the proper water, proper sanitization, proper healthcare system, then it is difficult, but it is improving. And I think much better than when I was kid. I was in a village, and now I could see it has drastically improved. We have the every places in a village, probably we have the toilet. We never had any proper toilet and sanitizer facility. Now every places in a village, every houses those have, and that is contributing. So enormous contribution to the development happen. But still we are lack of, probably behind. We need to move, even do much more what we have, and take care of this and stop this infection. Yes.
Okay. So the last question is the polyurethane coating kills any other kind of pathogens?
Yeah, we have done many pathogens. Like I have shown few only. If you see that various bacteria, they are the drug resistant. We have taken from the different patients as well, different places from the hospital, different gram-negative bacteria, gram-positive bacteria, different strains of bacteria. We have taken different fungi. Now we are showing that the viruses, influenza viruses, we have showing with the this COVID. And I believe that as we go along, probably we'll be able to even explore further. And I hope that it can take care other viruses, other pathogens as well.
Okay, so that is the end of the question answer. So thank you, Jayanta, for this very informative, timely talk. And also I take this opportunity in thanking all the speakers, Uday, Iswaramurthy, and Jayanta, for your wonderful lectures. And also I thank all the participants, particularly the students, for spending your time with us in this first session of the FCBS workshop. So I'm handing over the mic to Reggie or Joshi. We are exactly on time. I have 2 extra minutes to you. So use that minute.
Thank you, sir. Thank you very much. I would like to take this opportunity to thank Dr. Ajay Ghosh for wonderfully managing this session. And as he mentioned, we are right on time, and he always does that. So in fact, we have no words to express our thanks to him, because he was literally sitting in front of the computer from morning to evening, and he was attending or leading the RC meeting, very intense discussions until noon, and quickly went for lunch, and then came back, and then started attending this meeting, and he participated in all lectures and listened to it. So this shows that his commitment to science and science education, and especially to these programs, and how he leads all of us in doing these programs. So, sir, definitely you are an inspiration for all of us, and thank you for your guidance, help, and support. Thank you very much. And we also take this opportunity to thank Dr. Suresh Das and all the speakers of today's sessions. As you may know, that all of them gave lectures multiple times in this CBS, and they all take their time off of 3 days. They will come to Trivandrum and then interact with the participants. This year we are missing the direct interaction, especially the students used to have a very good time interacting with these experienced faculty members from prime institutes in India. So we take this opportunity to thank all our resource persons, and the participants also. They were staying with us even after this 3 hours. There are net restrictions and other things, and I thank all of you, and thank you again, and good night. Tomorrow's session again starts exactly at 4 p.m. like today. Thank you.
Thank you.
Thank you. Thank you, everybody. So thank
you.
Thank you. And bye-bye.
Thank you, Uday. You have to go back to Bangalore, huh?
Yes. I'm waiting for the eagle.
After this 3 hours, there are net restrictions and other things, and I thank all of you, and thank you again, and good night. Tomorrow's session again starts exactly at 4 p.m. like today. Thank you.
Thank you.
Thank you. Thank you, everybody. So thank
Thank
you.
you.
Thank you.